Welcome to the Sleepy Scientist, a calm corner of the universe where curiosity drifts gently like starlight. Tonight's journey takes us into the heart of the cosmos, to explore the great recipe behind everything we are and everything we see, the elements forged in stars. Before we set out, I would love to know where in the world you are listening from. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle explorations, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little constellation of listeners grow. I do hope this story soothes you toward rest. Though, fair warning, the universe has a habit of being a little too captivating. If you do find yourself wide awake at the end, at least you will have learned something wonderful about the stars. So let us begin with a quiet question to carry with you. How did the fiery hearts of stars manage to shape the very atoms of your own body? Long before Earth, before the seas, before even galaxies fully formed, the universe began with only the simplest of ingredients. Hydrogen and helium filled the void, drifting through the newborn cosmos in great, quiet clouds. On their own, these elements could not create oceans, mountains, or living things. Yet hidden within their simplicity lay the potential for astonishing complexity. It was the stars that unlocked this potential, each one a glowing furnace, compressing and reshaping matter at unimaginable scales. Within their blazing cores, the raw materials of the early universe were slowly transformed into the building blocks of everything that followed. Every breath of oxygen, every grain of sand, every trace of iron in your blood. All of it began as starlight, reshaped by fusion and scattered across the dark. This video is a journey into that cosmic recipe. We will wander through the slow chemistry of stars, the dramatic violence of supernovae, and the delicate alchemy that creates elements both common and rare. Along the way, we will uncover how these scattered ingredients came together to form Earth, to shape life, and eventually to make it possible for you to sit or lie here now, listening. It is a story that is at once scientific and profoundly human. For to know that our bones, our breath, and even the thoughts passing through our minds are bound to the same processes that light the night sky is to feel an unbroken connection to the cosmos itself. This is not just a tale of physics and chemistry. It is the quiet reminder that every one of us carries the imprint of stars. And so, let us step gently into the story of how the universe became more than simple gas, how fire gave birth to form, and how the heavens wrote the recipe for life. In the beginning, the universe was not the rich tapestry of worlds and wonders we see today. There were no mountains, no rivers, no trees bending in the wind. There were no galaxies spinning in their grand spirals or clusters of stars lighting up the night. What there was instead was a kind of cosmic simplicity. Imagine the universe as a kitchen that had only just opened its doors. The cupboards were nearly bare, stocked with only a few humble ingredients: hydrogen, helium, and just a pinch of lithium. This may sound like a disappointing start for a recipe meant to create everything from nebulae to Nobel Prizes, but it was exactly the beginning required. Out of these few ingredients, the entire universe would be built. To understand how, we must first rewind the cosmic clock to those first few minutes after the Big Bang. The Big Bang itself was not an explosion in the ordinary sense. It was space itself expanding from something unfathomably small and hot into the vastness we now inhabit. In those first moments, the conditions were so extreme that matter as we know it could not exist. Instead, the universe was filled with a seething soup of energy, particles and radiation, all dancing in chaotic motion. As the universe expanded, it cooled. In physics, cooling is a kind of permission slip. It allows things to slow down enough to join together. Within the first 3 minutes, protons and neutrons, the tiny building blocks of atomic nuclei, began to link up. It was here that the first chemical elements were born, though only in their simplest forms. Hydrogen came first. a single proton with an electron buzzing around it like a loyal companion. Helium followed, a little more sophisticated with 2 protons and 2 neutrons bound together, like hydrogen's older, sturdier sibling. And finally, lithium appeared, but only in trace amounts, barely enough to be noticed. This moment in cosmic history is called Big Bang nucleosynthesis. It lasted for only about 20 minutes, a fleeting instant in cosmic terms. Yet in that short time, the universe stocked its shelves with the lightest and most essential ingredients. Roughly 3/4 of all the normal matter became hydrogen, about 1/4 became helium, and a scattering of lithium was sprinkled in like cosmic seasoning. Now, one might ask, why stop there? Why not jump straight to carbon, oxygen, or iron? The stuff that feels more like the makings of a universe filled with complexity. The answer lies in the physics of stability. The universe, in those hot, dense early moments, could not hold together anything heavier. As soon as atoms larger than lithium tried to form, they would fall apart in the chaos. In a sense, the universe was too impatient, too energetic to attempt more elaborate creations. And so, it settled on a kind of elegant austerity. 3 main elements, hydrogen, helium, and lithium, would become the starting point. On the face of it, this may seem terribly limiting. After all, try cooking with only 3 ingredients and see how far you get. But the beauty of this simplicity is that it forced creativity. Out of these lightest elements, stars would eventually ignite, and stars would be the ones to cook up the rest of the periodic table. Hydrogen, the lightest element, deserves a special mention. It is the simplest atom possible, and yet it dominates the universe. Even today, billions of years later, hydrogen makes up the majority of all ordinary matter. Think of it as the flower of the cosmic kitchen, unassuming, abundant, and utterly essential. Without it, there would be no stars, because hydrogen is the fuel that allows them to burn. Helium, on the other hand, is a more refined ingredient. In balloons, it makes our voices squeaky, but in stars it acts as the ash left behind after hydrogen burns. When stars exhaust their hydrogen, helium takes centre stage as the next element in the chain of fusion reactions. It may not be as common as hydrogen, but it is just as vital to the recipe. Lithium, poor lithium, is the quiet underdog of this cosmic trio. It is present in only trace amounts from the Big Bang. In fact, astronomers have long puzzled over lithium, because the amount we see in the universe today is not quite what theory predicts. Some stars seem to have destroyed much of their lithium, swallowing it up in their fiery bellies. Others, curiously, appear to have created a bit more of it later on. Lithium, it seems, has always been a mysterious and slippery character in the cosmic story. It is remarkable to think that everything else we know and love, the oxygen in your lungs, the calcium in your bones, the silicon in the rocks beneath your feet, all came later. At the beginning, the universe was as plain as a bowl of broth, waiting for something to stir the pot. But there is a kind of wisdom in this simplicity. With only the lightest elements, the universe avoided overcomplicating its earlier stages. Hydrogen and helium are wonderfully stable, and that stability allowed them to persist through eons of cosmic evolution. They were the scaffolding on which the grander structures of galaxies could be built. Clouds of hydrogen and helium gathered under gravity's patient pull, forming the first stars and galaxies. Without those simple elements, there would have been no fuel for Starlight, no sparks to ignite the great cosmic fires. Sometimes the most extraordinary recipes begin with the plainest ingredients. In fact, that may be the most astonishing part of this story. From the simplest atoms came the groundwork for the immense variety we see today. Hydrogen and helium do not look like much, but give them time, gravity, and the right conditions, and they become stars, planets, oceans, and life itself. Think of the universe as a chef who begins with flour, water, and salt. At first glance, hardly a feast, but with patience and technique, bread rises, flavour develops, and nourishment appears. In the same way, the cosmos took hydrogen, helium, and lithium, and, through the patient artistry of stars, baked the complex world we now inhabit. So, the next time you look up at the night sky, remember that it all began in extraordinary simplicity. The dazzling lights above, the elements of your own body, the world around you, all trace back to a cosmic cupboard that once held only three things. Out of that bare beginning, everything else would follow. Simplicity, it seems, was not a limitation at all, but the perfect foundation for a universe destined to be anything but plain. Stars are not just lights in the night sky. They are the universe's kitchens, gathering up the simplest ingredients and slowly transforming them into something far richer. If the cosmos began with only hydrogen, helium, and a whisper of lithium, it was stars that took those plain beginnings and cooked them into the banquet of elements that make up worlds and living beings. To understand how this happens, imagine the recipe book of the universe as one written not with ink but with heat, pressure, and time. The first step in this cosmic cooking is gravity. Gravity is the universe's quiet but relentless chef. Clouds of hydrogen and helium drift through space, vast and seemingly shapeless, but gravity is always at work, tugging on every atom. Over millions of years, this invisible pull gathers the scattered gas into clumps, then into denser knots, and eventually into massive spheres. The bigger the cloud, the stronger the pull, and the faster it collapses inward. As the gas falls inward, it heats up. Pressure builds at the centre, like the tension in a tightly wound spring. This is the universe's way of preheating the oven. Stars do not need matches or sparks to light. They simply compress themselves until their cores become so hot and dense that nuclear fusion begins. At that point, the kitchen is open and the cooking can truly start. Fusion is the secret recipe. In the simplest terms, it is the process of taking two light atomic nuclei and forcing them together to make something heavier. But it is not as easy as it sounds. Protons, the positively charged particles at the heart of atoms, naturally repel one another. It is like trying to push the north poles of two magnets together. Yet in the core of a star, the pressure and temperature become so intense that protons have no choice but to overcome this resistance. Once they collide, they fuse, releasing enormous amounts of energy in the process. This energy is the light and warmth we see from stars. Every twinkle in the night sky is the outward sign of nuclear fusion happening far away. But the process is also far more than just a light show. It is the careful alchemy by which stars create new elements, little by little, over spans of time so vast that human history seems like a passing thought. The main dish of most stars is hydrogen fusion. In our own sun, billions upon billions of hydrogen atoms are fused every second, producing helium. Each time this happens, a tiny fraction of mass is lost, transformed into pure energy according to Einstein's famous equation. This is why stars can shine for billions of years without running out of fuel. Their recipe is not fast food. It is slow, steady, and incredibly efficient. Think of a star's core as a slow-cooking oven, one that never turns off. The heat is constant, the pressure unwavering, and the recipe is designed to take time. This is not a hurried meal. It is more like a stew left to simmer gently, with flavours deepening over the ages. The star's outer layers act like a lid, keeping the core stable so the fusion can continue without interruption. But hydrogen is only the appetizer. As the supply runs low in the core, a star adjusts its recipe. Gravity tightens its grip once more, compressing the star until the temperature rises high enough for helium fusion to begin. Now the star begins to cook carbon and oxygen, the essential ingredients for life. Larger stars go even further, fusing heavier and heavier elements in a layered structure that resembles the rings of an onion. Each shell burns a different fuel, with hydrogen on the outside, helium beneath it, carbon deeper still, and so on, down to silicon near the core. In the largest stars, the kitchen becomes a roaring furnace. These giants can reach temperatures of hundreds of millions of degrees in their cores, enough to fuse elements all the way up to iron. Every step in this process releases energy, helping the star hold itself up against gravity. It is a balancing act. Fusion pushes outward, gravity pulls inward, and the star endures for as long as those forces remain in harmony. Our Sun is modest by comparison. It is not destined to fuse carbon into heavier elements or to blaze with the intensity of a supergiant. Instead, it quietly spends its long life transforming hydrogen into helium, a dependable oven working at a steady pace. Yet even this gentle process is enough to bathe our planet in light and warmth, powering everything from the growth of trees to the beating of hearts. One of the most beautiful things about this cosmic cooking is its patience. Stars are not in a rush. Some live for only a few million years, burning through their fuel quickly like a chef who cannot resist turning the heat up too high. Others, like red dwarfs, burn their hydrogen so slowly that they can live for trillions of years, far longer than the universe has existed so far. These stars are the true masters of slow cooking, stretching their ingredients to last through unimaginable spans of time. It is tempting to think of stars as static, unchanging pinpricks of light, but they are anything but still. Inside, they are busy kitchens, bustling with activity we cannot see. The fusion reactions happen on scales so vast that numbers lose their meaning. Imagine a spoonful of the sun's core. It would weigh more than an entire mountain, and it would be hotter than any furnace we could build on Earth. Yet stars manage all of this with a kind of serene composure, their light spreading quietly through space. The comparison to a kitchen is not just poetic, it is literal in the sense that stars are where the ingredients of everything else are prepared. Without them, the universe would remain a bland broth of hydrogen and helium. With them it becomes a feast of elements: carbon for life, oxygen for air, silicon for rocks, iron for blood and bridges, and countless others. Stars are chefs that work on cosmic timescales, and their recipes feed galaxies. And so, when you look up at the night sky and see the soft glow of starlight, remember that you are witnessing an oven at work, hidden behind billions of miles of gas. Those lights are not distant decorations. They are kitchens that have been running for billions of years, perfecting the recipe that eventually produced you. From a handful of simple ingredients, stars have created a universe full of complexity. It is a process at once relentless and gentle, violent in scale yet graceful in result. What could be more astonishing than that? That the quiet twinkle you see above is in truth the light of atoms being transformed, of recipes unfolding in silence across the dark. Every star you see is both a furnace and a promise, that even the simplest ingredients given time and patience can become something extraordinary. Fusion is the quiet miracle that powers the stars. At its heart, fusion is the art of taking the simplest of atoms and pressing them so tightly together that they merge into something new. It is alchemy in the truest sense, though not the kind imagined by medieval scholars in candlelit rooms. This is not about turning lead into gold with mysterious potions, but about nature itself finding a way to build complexity from simplicity. The story begins with hydrogen, the most basic atom in the universe, a single proton at its core, one electron circling it like a faithful moon. Hydrogen is everywhere, and it is the starting point for nearly everything. Yet as modest as it seems, when 4 atoms of hydrogen are persuaded to fuse in the core of a star, they transform into helium, releasing a dazzling amount of energy. It is as if hydrogen has been hiding a secret all along, the ability to unleash the light of stars. But how does this happen? Protons are positively charged, and positive charges repel each other. It is the same as trying to push 2 magnets together when their like poles face one another. The harder you push, the more stubbornly they resist. In ordinary conditions, fusion simply does not happen. But inside a star, conditions are anything but ordinary. Temperatures climb to millions of degrees, and the pressure is unimaginably high. At such extremes, hydrogen nuclei are hurled about so violently that they smash into each other before they can fully repel. When they collide with enough force, the strong nuclear force, one of the fundamental forces of nature, takes over and binds them together. The strong nuclear force is a peculiar thing. At long distances it does nothing. At very short distances, however, it becomes the most powerful force known, gluing protons and neutrons together with incredible strength. Fusion is possible only when atomic nuclei are brought close enough for this force to act, and in the dense, fiery heart of a star, that is exactly what happens. The result is helium, an atom made of 2 protons and usually 2 neutrons. The math, however, does not quite add up. When 4 hydrogen nuclei fuse to make helium, the helium nucleus weighs a little less than the sum of its parts. That missing mass has not vanished. It has been transformed into energy, according to the famous equation E equals mc squared. This is why fusion is so powerful. Even a tiny loss of mass can release an enormous burst of energy. Multiply that by the countless reactions happening every second in a star's core, and you have the light and heat that streams across space to reach us. For millions or even billions of years, hydrogen fusion is the steady heartbeat of a star. But stars, like chefs with limited ingredients, eventually run low on hydrogen in their cores. When that happens, gravity steps in again, squeezing the core tighter and heating it further until a new recipe becomes possible: helium fusion. Helium fusion is more challenging than hydrogen fusion because it requires even higher temperatures to overcome the repulsion between nuclei with 2 protons each. But when the star manages it, something remarkable emerges: carbon. In a reaction called the triple alpha process, 3 helium nuclei combine to form a single carbon nucleus. Carbon is the backbone of life, the versatile element that forms chains, rings and frameworks for the molecules of biology. Every carbon atom in your body was once forged in the hot heart of a star that learned to fuse helium. From carbon, the fusion ladder continues upward. Add another helium nucleus, and carbon becomes oxygen. With further steps, stars can build neon, magnesium, silicon, and sulfur. The sequence is like a slow cosmic recipe, with each new layer of fusion producing the ingredients for the next. In the most massive stars, these reactions occur in shells around the core, each layer burning a different fuel, stacked like the layers of an onion. But there is a limit to how far this alchemy can go. The key to fusion's power is that the resulting atom weighs slightly less than the parts that created it, with the difference turned into energy. As long as that trade works, stars can shine, yet when the fusion chain reaches iron, the story changes. Iron is the cosmic full stop. Why iron? The reason lies in the binding energy of nuclei. For lighter elements, fusing them together makes a more tightly bound nucleus and releases energy. For heavier elements beyond iron, the opposite is true. Trying to fuse them requires more energy than it produces. Iron sits at the perfect point of stability, a kind of cosmic dead end. Fusion can climb no higher up the periodic table, at least not inside an ordinary star. When a massive star builds up an iron core, it faces an inevitable crisis. Fusion can no longer provide the outward push to balance gravity's inward pull. The core becomes unstable, collapsing under its own weight in a matter of seconds. This collapse often triggers a supernova, one of the most violent events in the universe, where the heavier elements beyond iron are finally created in a furious burst of energy and chaos. But in the quiet interiors of stars, iron is as far as fusion will go. Our own sun will never reach that stage. It is not massive enough to push fusion beyond helium into the heavier elements. Instead, it will eventually shed its outer layers, leaving behind a white dwarf, a stellar ember made mostly of carbon and oxygen. But in larger stars, the journey from hydrogen to iron plays out like an elaborate recipe, each stage more intense than the last, until gravity demands its dramatic finale. The alchemy of fusion is one of the universe's most astonishing tricks. It turns empty space filled with simple hydrogen into galaxies glowing with stars, and those stars in turn into the elements of planets and people. It is relentless, patient, and beautiful. Without it, the universe would still be a thin mist of hydrogen and helium, and life would never have emerged. When you think of fusion, do not picture a violent explosion or a hurried process. Think instead of a quiet fire that burns with absolute steadiness, one that takes billions of years to complete its work. It is not the blaze of a match, but the long, slow glow of an eternal hearth. It is this fire that has filled the universe with light and with the elements of life. And somewhere within you, in the carbon of your cells and the oxygen in your blood, fusion's fingerprints remain. You are, in the most literal sense, the product of the alchemy that stars have been performing since the dawn of time. Fusion may stop at iron, but its legacy reaches far beyond, written into every atom that makes you who you are. The periodic table is often thought of as a human invention, an orderly grid designed to tame the chaos of chemistry into neat rows and columns. But in truth, it is less a creation than a discovery. Its shape and order reflect the hidden structure of the cosmos itself. Every box on that table tells a story of origin, and most of those stories trace back to the hearts of stars, the violence of supernovae, or the rare collisions of neutron stars. What seems like a classroom chart of coloured squares is in reality the recipe of the universe, written in the language of atoms. Begin at the far left with hydrogen. This is the simplest and most abundant element, born in the minutes after the Big Bang. Its single proton is the starting point for almost everything. Just beside it sits helium, also formed in those first cosmic instants, filling balloons on Earth, but filling the vast reaches of space with lightness and stability. Together, hydrogen and helium make up about 99% of all normal matter in the universe. If you had to summarize the cosmos in 2 words, those names would suffice. But the table stretches far beyond them. Carbon, nitrogen, oxygen, the stuff of life, occupy its center like familiar neighbors. They too began in stars, helium nuclei fused into carbon and carbon into oxygen in the fiery cores of aging stars. Nitrogen formed as an intermediate, often in the lives of massive stars, and later joined the chemistry of living cells. These elements are not scattered randomly on the table. They occupy a family group that reflects their shared stellar origins, like siblings from the same ancestral line. Move further along and you encounter silicon, magnesium and iron, the building blocks of planets. Silicon and oxygen form rocks and sand, magnesium strengthens minerals, and iron anchors the cores of worlds. These too are the children of stars, forged in layers of fusion that build up as stars near the end of their lives. Iron, as we have seen, is the great stopping point. It represents the limit of stellar alchemy, the heaviest element that can be created through normal fusion in a star's core. Beyond iron, the periodic table shifts into a new story. For the heavier elements, gold, platinum, uranium and the like, the usual stellar kitchens are not enough. These require extraordinary events, brief and violent, to come into existence. When a massive star explodes as a supernova, the temperatures and pressures soar to levels that ordinary fusion could never achieve. In those final seconds, the outer layers of the star are bombarded with a storm of neutrons, and new heavy elements are built in a rush. The gold in a wedding ring, the iodine in your thyroid, the uranium in nuclear fuel. Each of these atoms was born in an explosion that tore a star apart. Rarer still are neutron star collisions. Imagine 2 remnants of massive stars, each one a sphere of matter so dense that a teaspoon of it would outweigh mountains. When such objects spiral together and crash, the universe momentarily unlocks conditions unlike any others. In those fleeting instants, torrents of neutrons stream into atomic nuclei, creating some of the heaviest and rarest elements in existence. Platinum, for instance, owes much of its cosmic abundance to such collisions. These are not everyday events. Entire galaxies may go millions of years without witnessing one, and yet the atoms from those rare moments eventually scatter across space, waiting to be incorporated into planets and people. The periodic table, then, is not just a list of elements, but a cosmic map of processes. Hydrogen and helium from the Big Bang, carbon, oxygen and silicon from stellar fusion, gold and platinum from cataclysmic explosions and collisions. Each square is stamped with a kind of cosmic address, a record of where in the universe it first came into being. It is worth pausing to reflect on the elegance of this arrangement. The periodic table was designed by humans in the 19th century, long before we knew the stellar origins of its contents. Dmitry Mendeleev, the Russian chemist who first laid it out, could not have guessed that the order he arranged by chemical behavior mirrored the deep history of the cosmos. His table grouped elements by the patterns of their reactivity, but those same groupings also reflect the patterns of their birth in stars. It is as if, in sorting atoms by their earthly properties, we accidentally revealed their heavenly lineage. Consider oxygen, occupying its place alongside sulfur and selenium. All of these belong to the same family column, sharing chemical traits. Yet they also share a cosmic story, each born from the fusion of helium and carbon deep in stars. Or take the noble gases, helium, neon, argon. Their very reluctance to react with anything mirrors the fact that they were created in stellar processes that left them remarkably stable. This view of the periodic table transforms it from a chart of numbers into a kind of family tree. Each row marks a generation of cosmic creation, each column a branch of related elements that share a common path. The table becomes less about memorization and more about storytelling. You can read it like a history book written in symbols. It also emphasizes a humbling truth. The universe is not random in its generosity. The most abundant elements are those most useful for structure and life. Hydrogen provides fuel for stars and water for life. Carbon forms countless molecular frameworks. Oxygen allows for respiration and oceans. Silicon and iron build planets. Even the rarer elements have their roles. Phosphorus for DNA, iodine for hormones, copper for blood chemistry in some creatures. It is as though the cosmos, in its patient cooking, produced not just elements, but a toolkit for complexity. And yet, this is not destiny, but physics. The shapes of nuclei, the stability of bonds, the thresholds of energy, these physical rules guide the recipe. The table reflects what is possible, and the universe has explored those possibilities fully. Nothing in the table is wasted. Even the rarest elements appear in traces that influence biology, geology, or technology in ways we continue to uncover. When you next see the periodic table, do not think of it as a classroom chart. See it instead as a cosmic atlas. Each symbol is a destination, each number a set of coordinates pointing to the furnace or explosion that gave it birth. The table is not simply about chemistry, it is about cosmology, astrophysics, and the grand history of matter itself. So much of science is about finding order in apparent chaos. The periodic table achieves this with breathtaking clarity. It tells us that the atoms of our bones, our oceans, our air, our gold jewellery, and even the uranium powering reactors all came from different chapters of the universe's story. Some were written in calm stellar cores, others in the explosive deaths of stars, and still others in the rarest of cosmic collisions. Together they make the narrative whole. The table of elements is not just a tool for scientists, it is a reminder that every piece of matter, no matter how ordinary, has a cosmic origin. When you pick up a stone, you are holding a record of stellar fusion. When you drink water, you're tasting the aftermath of ancient hydrogen and oxygen unions. When you glance at a golden ring, you're glimpsing the echo of a neutron star collision that may have happened billions of years ago in some forgotten corner of the galaxy. The periodic table is the universe's autobiography, condensed into rows and columns. To read it is to read the story of how stars lived, died, and scattered their gifts. To understand it is to understand not just chemistry, but the deep kinship between human life and the cosmos that created it. And to stand in awe of it is only natural, for in those little squares lies the quiet truth that everything around you and everything within you belongs to the same cosmic recipe. Carbon is one of those elements that seems almost too humble for the role it plays. It is not flashy like gold, not as immediately obvious as oxygen, and not as abundant as hydrogen. Yet carbon quietly holds the title of life's architect. Without it, there would be no chains of DNA, no proteins folding into delicate shapes, no sugars to fuel our cells, no forests of trees stretching toward the sky. Carbon is the backbone of biology, the central pillar upon which life as we know it is built, and the story of how it came to be is as extraordinary as the role it plays. The origins of carbon begin in the blazing heart of stars. Hydrogen fusion may keep stars alight, but it is helium fusion that makes carbon possible. When a star runs low on hydrogen at its core, gravity presses inward, heating the stellar furnace to new extremes. At around 100 million degrees, a special process begins, known as the triple alpha reaction. The name may sound technical, but the idea is elegantly simple. Helium atoms, also called alpha particles, are incredibly stable. Yet under immense pressure and temperature, they can be persuaded to fuse. First, two helium nuclei collide to form beryllium, but this arrangement is unstable and usually falls apart almost instantly. However, in the rare moments when a third helium nucleus joins in before beryllium decays, the three merge to form carbon. It is like catching lightning in a bottle, a fleeting moment of chance that, against the odds, results in stability. What makes this process even more astonishing is how delicately balanced it is. The odds of three helium atoms colliding at once are tiny. For this to happen often enough to create the abundance of carbon we see today, the laws of physics must align with uncanny precision. If the energy levels in carbon were even slightly different, the triple alpha process might not occur at all. Some scientists have pointed to this as an example of fine-tuning in the universe. Others see it as the natural outcome of physical laws we're still learning to understand. Either way, the result is the same. The cosmos found a way to create carbon, and in doing so, it created the possibility of life. Carbon is not only born in stars, it is also scattered by them. When a star of moderate size, like our Sun, reaches the end of its life, it gently sheds its outer layers, releasing carbon into space in soft waves of gas and dust. In larger stars, the release is far more dramatic, with supernova explosions blasting carbon and other elements across the galaxy. Over billions of years, these scattered atoms drift together, forming clouds that will one day become new stars, planets, and even living organisms. What makes carbon so special is not just that it exists, but what it can do. Its unique chemistry allows it to form bonds in 4 directions at once, creating an astonishing variety of structures. Carbon atoms can link together in long chains, form rings, or branch out into complex frameworks. No other element offers quite the same combination of stability and flexibility. It is like having a box of building blocks that can be assembled into almost any shape imaginable. Because of this, carbon chemistry, or organic chemistry as it is called, is the foundation of life. Carbon forms the backbone of DNA, the spiral staircase that carries genetic information. It constructs proteins, the molecular machines that perform nearly every function in cells. It creates carbohydrates and fats, storing energy and shaping membranes. Even the simple act of breathing relies on carbon dioxide, a molecule in which carbon is bound to oxygen. The element is so central that when scientists search for life beyond Earth, they often look for signs of carbon-based chemistry as their first clue. Yet carbon is not confined to biology. It shows its versatility in countless other forms. In one arrangement, carbon atoms bond in flat sheets, creating graphite, soft enough to leave marks on paper. In another, they lock into a rigid lattice, forming diamond, one of the hardest substances known. Carbon can also twist into hollow spheres called fullerenes, or roll into cylinders known as nanotubes, each with strange and useful properties. It seems that carbon never stops offering new surprises, its structures ranging from the delicate to the indestructible. The presence of carbon on Earth is also tied to our planet's long and delicate balance. Carbon cycles between the atmosphere, the oceans, the soil, and living things in a grand planetary rhythm. Plants take in carbon dioxide through photosynthesis, turning it into sugars and releasing oxygen. Animals eat the plants, breathe out carbon dioxide and return it to the air. Meanwhile, carbon settles into rocks, dissolves in oceans, and even escapes into space over eons. This circulation ensures that carbon remains available in forms life can use, while also regulating Earth's climate. If carbon is the architect of life, then Earth is its construction site, and the balance of the carbon cycle is the blueprint that allows everything to function. When this cycle tips too far, climates shift, ecosystems change, and the conditions for life can become fragile. In this way, carbon is both a gift and a responsibility, reminding us of our connection to the stars and to the planet beneath our feet. What is especially poetic is that the carbon in your body, in every breath, every heartbeat, every thought, began in the death throes of stars billions of years ago. The atoms forming the sugars fueling your brain were once fused in a stellar core. The carbon woven into your DNA spiraled through the galaxy before settling on Earth. In this sense, you're not simply made of stardust in a general way. You're made of carbon atoms forged in fire, carried across space, and carefully assembled into life. It is no exaggeration to say that without carbon, the universe would be unrecognizable. Stars would still shine, galaxies would still spin, but life, at least as we know it, would not exist. There may be other possibilities. Silicon-based life has been imagined, for example, but nothing rivals carbon's extraordinary versatility. It is the quiet architect not because it demands attention, but because it patiently builds everything that matters. Perhaps the most profound truth about carbon is that it demonstrates how something simple can give rise to complexity. A single kind of atom, no larger than a whisper, holds the power to create infinite forms. From the elegance of a diamond to the spirals of DNA, carbon is everywhere, shaping the visible and the invisible alike. So the next time you breathe out, consider the carbon dioxide drifting from your lungs. Those atoms were born in a star, billions of years before Earth formed. They may one day find themselves part of a tree, a shell, a mountain, or another living being. Carbon's story is not only the story of life, but of continuity, an endless thread connecting stars, planets, and people. It is the quiet architect of existence, always working, never boasting, building the structures of the cosmos one bond at a time. Oxygen is one of the most familiar elements in our daily lives, and yet its origins are as strange and spectacular as anything in the cosmos. It is the air you breathe, the invisible companion of every lungful that keeps your cells alive. It is locked into water, shaping oceans, rivers, and even the rain falling from the sky. It is embedded in rocks and minerals, forming much of the crust of the earth beneath your feet. If carbon is the architect of life, oxygen is the breath, the spark that keeps the whole construction running. And like so much else, it began in the blazing interiors of stars. The story of oxygen's birth begins where carbon's leaves off. In the fiery core of a star that has already mastered helium fusion, the process does not stop at creating carbon. Helium atoms can continue to collide with carbon nuclei, sticking together and forming oxygen. It is a kind of stellar layering where the triple alpha process builds carbon, and then the carbon serves as scaffolding for oxygen to form. The physics is elegant in its simplicity, yet the scale is anything but simple. Temperatures in the hundreds of millions of degrees are required for helium nuclei to slam into carbon with enough force to merge. Oxygen, once formed, is stable, and it tends to accumulate in large quantities inside stars. In fact, oxygen is the third most abundant element in the universe, after hydrogen and helium. The atoms that now rush in and out of your lungs were once trapped in stellar cores, forged in the pressure and heat of stars long gone. When those stars reached the end of their lives, they released oxygen into space, scattering it like seeds on a cosmic wind. Some was blown gently into the galaxy when small stars shed their outer layers, and some was hurled outward violently in the shockwaves of supernovae. Over time, those atoms became part of new solar systems, planets, and eventually living organisms. On Earth, oxygen's presence has defined almost everything. It makes up about 1/5 of our atmosphere, yet in its elemental form, free to breathe, it was not always so abundant. For the first couple of billion years of Earth's history, the atmosphere contained little to no oxygen. The world was rich in carbon dioxide, methane and nitrogen, but oxygen was locked away in minerals or dissolved in the oceans. Life began without it, relying on chemical pathways that did not require oxygen at all. Then something extraordinary happened. Microorganisms evolved the ability to use sunlight to split water and release oxygen, the process we know as photosynthesis. At first, the oxygen they produced reacted quickly with iron in the oceans, rusting the seas red and forming vast deposits of iron ore. Only after millions of years did oxygen begin to accumulate in the atmosphere, triggering what scientists call the Great Oxidation Event. It was a turning point not just for Earth, but for life itself. Oxygen allowed for more efficient ways of releasing energy, paving the way for complex multicellular organisms. Every animal that breathes today, including us, owes its existence to that moment when oxygen began to fill the skies. The connection between stellar birth and planetary breath is a profound one. The oxygen atoms created in stars were scattered across the galaxy, gathered into clouds, and eventually built into Earth. Once here, they became part of water, carbon dioxide, and countless minerals. Then, through the creativity of life, oxygen was released back into the air. What stars began, life continued. The breath in your lungs right now is the end of a chain that began billions of years ago in the heart of a star. Oxygen is versatile in a way that makes it indispensable to life and geology alike. In water, it bonds with hydrogen, creating the solvent that makes chemistry mobile. In rocks, it bonds with silicon to form silicates, the most common minerals in Earth's crust. In your body, it bonds with iron inside hemoglobin, hitching a ride through the bloodstream to fuel your cells. Oxygen's talent lies in its ability to form stable yet reactive bonds, participating in the delicate dance of chemistry that keeps both planets and living systems dynamic. Even the act of breathing is an exchange written in the language of oxygen. When you inhale, oxygen enters tiny sacs in your lungs and crosses into the blood. There it binds to hemoglobin and is carried to every corner of the body. In your cells, oxygen helps break down sugars, releasing energy in a process far more efficient than anything without oxygen. The waste, carbon dioxide, travels back the other way and is exhaled. This quiet rhythm, in and out, is a direct link between the stellar origins of oxygen and the daily miracle of being alive. On a planetary scale, oxygen is both a giver and a taker. It fuels fire, erodes rocks, rusts metals, and shapes landscapes. The very mountains crumble under its slow chemistry. Without oxygen, there would be no flames, no corrosion, no blue skies overhead. The tint of Earth's atmosphere, the sparkle of water, the glow of a sunset, all of these are coloured by oxygen's presence. What makes oxygen even more intriguing is how rare free oxygen seems to be elsewhere. Astronomers searching for life on other planets often look for signs of oxygen in their atmospheres. Because oxygen so readily reacts with other elements, it does not linger unless it is constantly replenished, usually by biological processes. If we ever detect an exoplanet with abundant oxygen in its air, it could be one of the strongest hints that life exists there. Oxygen becomes not just the breath of stars, but also a beacon of life across the cosmos. It is easy to take it for granted. Every breath feels effortless, unremarkable, a background hum to life. Yet each molecule is a survivor of a journey across time and space, forged in stellar fire, scattered across galaxies, trapped in stone, freed by microbes and drawn into your lungs. Oxygen is not ordinary at all. It is a traveller that has moved through epochs and processes beyond imagination before becoming part of your story. In the end, oxygen is not only a chemical element, it is a thread weaving together the history of stars, the evolution of Earth, and the daily rhythm of life. It fills your lungs as quietly as it fills oceans and skies, always present, always working. To breathe is to participate in a cosmic cycle billions of years in the making. The stars gave us oxygen, and life gave it back to the air, creating a loop that ties us to the universe in every breath. When you next take a deep breath, pause for a moment. You're inhaling the legacy of stars. The air that sustains you was once trapped in a stellar core, released in a burst of light and energy, and carried across space until it became part of this world. Oxygen is the universe's quiet reminder that even the simplest act, breathing, is an echo of the cosmos itself. Iron is the universe's punctuation mark, the element that signals an ending rather than a continuation. For stars, it is the final stop on a long and fiery journey of fusion, the place where stellar cooking suddenly halts. To understand why this is so and why iron carries such dramatic consequences is to glimpse one of the most remarkable truths of cosmic evolution. In the kitchen of a star, fusion works like a slow but steady recipe. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and so on. Each step releases energy, and that energy keeps the star shining while also pushing outward against the immense inward pull of gravity. It is a delicate balancing act. Without the outward pressure from fusion, gravity would crush the star inward. Without gravity, fusion could not be sustained. The two forces hold each other in check and the star enjoys a long, steady life. But this delicate arrangement only works as long as fusion produces energy. Once a star begins to build an iron core, everything changes. Unlike lighter elements, which release energy when they fuse, iron does not. Its nucleus is so tightly bound that fusing it into heavier elements actually consumes energy rather than releasing it. In a sense, iron is the cosmic full stop, the point where nature's recipe book simply runs out of instructions. The physics behind this lies in what scientists call binding energy, the measure of how strongly protons and neutrons are held together in a nucleus. Lighter elements like hydrogen or helium have relatively low binding energy, so when they fuse, the resulting nucleus is more stable, and some mass is converted into energy. Iron, however, sits at the peak of stability. Its nucleus is already as tightly bound as possible. No further gain in stability can be made by fusing it, so no energy is released. Beyond iron, fusion becomes an energy drain, an impossible bargain for a star to sustain. This poses a crisis for massive stars. As long as they are fusing lighter elements, they produce the energy needed to keep gravity at bay. But once iron builds up in the core, fusion stalls. Gravity does not stall, though. It continues pressing inward with relentless force. The star no longer has any outward push to counter it. The result is catastrophic collapse. The collapse of a star's core is one of the most violent events in the universe. Imagine a core the size of Earth, made of iron and heavier elements, suddenly giving way under its own weight. In less than a second, it implodes, crushing atoms until protons and electrons merge into neutrons. The core becomes an unimaginably dense ball of neutrons, so compact that a teaspoon of it would outweigh mountains. Around this collapsing heart, the outer layers of the star fall inward, only to rebound off the newly formed neutron core. The shock wave tears outward, ripping the star apart in a blinding explosion, a supernova. The irony is that although iron marks the end of fusion, it is also the gateway to new creation. In the furious chaos of a supernova, the energies are so extreme that elements heavier than iron can finally be formed. Gold, silver, uranium, and dozens of others are born in the seconds after the collapse, forged in the neutron-rich storm. The iron full stop becomes the doorway to a new paragraph in the universe's story. Iron itself, though, is everywhere. It forms the inner core of Earth, giving our planet its magnetic field and helping protect life from harmful cosmic radiation. It flows in your veins as hemoglobin, carrying oxygen from your lungs to your cells. Every breath you take depends on iron's ability to bind oxygen, and every movement of a compass needle depends on the great reservoir of iron at Earth's centre. Iron is the element that signals stellar death, yet it is also the element that makes life on Earth possible. It is worth pausing to think of the chain of events that placed iron in your blood. Billions of years ago, a star many times the size of the Sun lived its life, burned through its lighter elements, and built up an iron core. When it could no longer resist gravity, it collapsed and exploded. That explosion scattered iron across space, eventually mixing into the cloud of dust and gas that became our solar system. From that ancient star's death, Earth inherited its iron, and you inherited the iron that carries oxygen through your body at this very moment. Without a long-dead star, you would not be breathing. The presence of iron on the periodic table, then, is not just a matter of chemistry, but of drama. Every atom of iron around you is a relic of collapse, a survivor of violence. When you hold a simple nail, you're holding the remains of a star's last breath. When you pick up a stone streaked with iron ore, you're touching the memory of a supernova. And when you feel your own pulse, you're sensing iron atoms at work, part of the endless chain that ties your life to the lives of stars. In literature, a full stop signals an ending, but in cosmic terms, the iron full stop is more like a transition. For the star that created it, it is the end, the collapse, the explosion, the dispersal. But for the universe as a whole, it is the beginning of new complexity. The death of a star plants the seeds of new worlds, new chemistry, and eventually new life. Iron is both final and fertile, destructive and creative. Stars may be patient cooks, but they cannot cook forever. Iron tells them their recipe has reached its conclusion. Gravity, never patient, takes over, and in doing so writes one of the most spectacular chapters of the universe's history. Without iron's stubborn stability, supernovae would not occur, heavy elements would not exist, and Earth itself might never have formed. So iron is not simply another element in the table. It is the hinge upon which the balance of stars swings. It is the signal that a star's kitchen is closing, the curtain falling on its performance. And yet it is also the spark that ensures the show goes on elsewhere, scattering the ingredients for new stars, new planets, and new beings. In your veins and in your planet's core, in tools and in towering skyscrapers, iron is everywhere, carrying the memory of stars. It is the cosmic full stop, but also the pause before a new sentence begins. The reminder that every ending in the universe is only ever a beginning in disguise. There are few sights in the universe as dramatic as a supernova. To the eye, it appears as a sudden brightening of a star, outshining entire galaxies for a brief moment. To the universe, it is the end of a long story and the beginning of many others. A supernova is both destruction and creation, a stellar death that scatters the ingredients of life across the cosmos. It is the explosive punctuation at the end of a star's sentence, and yet it is also the spark that lights new ones. To understand why stars sometimes meet such violent ends, we must step back into their kitchens. For millions or billions of years, a massive star steadily cooks lighter elements into heavier ones, stacking layers like the rings of an onion. Hydrogen at the outermost layer fuses into helium. Deeper within, helium fuses into carbon and oxygen. Even further inside, heavier elements like neon, magnesium and silicon form. At the very core lies iron, that stubborn full stop where fusion can go no further. For the star, this is a catastrophe. Fusion has been its only way to hold back gravity, its only defense against collapse. Once the core fills with iron, no more energy can be extracted. Gravity seizes its chance, and the star's core implodes. Imagine an object the size of Earth collapsing into a sphere only a few kilometers wide in less than a second. The matter falls inward with unimaginable force, protons and electrons squashing together to form neutrons. This sudden stop is like dropping a boulder into a still pond, sending shockwaves outward. The star's outer layers rebound off the dense neutron core, and the result is an explosion so powerful that it can briefly outshine billions of stars combined. This is the moment of a supernova. To distant observers, it is a sudden burst of brilliance in the night sky. To the universe itself, it is a furious storm of energy and particles, tearing atoms apart and forging new ones in their place. In these few seconds of chaos, elements heavier than iron are created in abundance. Gold, silver, iodine, uranium. These atoms cannot be made in the gentle simmer of a normal star. They require the violence of a supernova to exist. The ring on your finger, the trace of iodine in your body, the uranium buried deep in the Earth's crust. All of it was born in the fire of such explosions. Supernovae are rare on the human timescale. In a galaxy like the Milky Way, one might occur only once or twice in a century. Yet when they do happen, their effects ripple for eons. The shock waves from a supernova sweep up clouds of gas and dust, compressing them and sometimes triggering the birth of new stars. They seed the interstellar medium with heavy elements, ensuring that future generations of stars and planets are enriched with the chemistry needed for life. In this way, every supernova is both an ending and a beginning, the death of one star giving rise to countless others. On Earth, we are distant witnesses to this process. Ancient astronomers recorded sudden new stars appearing in the sky, shining brightly for weeks or months before fading. The most famous may be the supernova of the year 1054, which created the Crab Nebula and was observed by Chinese and Middle Eastern scholars. To them, it must have seemed like a celestial omen. Today, with telescopes and satellites, we see these events in greater detail, watching stars explode across the cosmos and measuring the elements they produce. The debris of a supernova is a spectacular sight. Expanding clouds of glowing gas stretch across light years, their colours revealing the elements they contain. Red glows with hydrogen, green with oxygen, blue with hotter, rarer elements. These nebulae are not just pretty remnants, they are the raw material for future worlds. The atoms blasted into space will one day settle into new solar systems, forming rocky planets, oceans and living creatures. Each glowing tendril of gas is a promise of things to come. Supernovae also play a quieter role in shaping the universe we see. Their shockwaves stir galaxies, distributing matter and influencing the formation of new stars. Without them, galaxies might stagnate, their chemistry locked in endless simplicity. With them, galaxies are enriched, dynamic, and alive with possibilities. In a sense, supernovae are the gardeners of the cosmos, clearing old growth and scattering the seeds of new. One of the most fascinating things about these explosions is how much they connect us to the stars. The iron in your blood, the calcium in your bones, the copper in your nerves, all of it was hurled into existence by stars dying in supernovae long before Earth was formed. To look at yourself is to look at a collection of atoms that once blazed in the heart of a dying sun. You are quite literally the aftermath of an explosion. Yet despite their violence, supernovae are not reckless events. They follow the laws of physics with precision. Collapse, rebound, explosion. Each step is dictated by the rules of matter and energy. It is nature at its most spectacular, but also at its most orderly. Out of chaos comes creation, and out of destruction comes renewal. There are even different varieties of supernovae, and each with its own story. Some are the deaths of massive stars collapsing under their own gravity. Others occur when a white dwarf star steals matter from a companion until it can no longer sustain itself, igniting in a thermonuclear blast. The details vary, but the outcome is always the same: a brilliant explosion that spreads the products of stellar fusion into the cosmos. If you could stand safely near one, though of course you could not, you would see light brighter than entire galaxies, hear nothing in the vacuum of space, and feel radiation that could sterilize worlds. From afar, though, the beauty is undeniable. Supernovae remind us that the universe is not static. It changes, it evolves, and it creates through cycles of birth and death. Think for a moment about the sheer improbability of it all. A star forms from clouds of hydrogen, fuses elements in its heart, reaches a limit, collapses, and explodes. That explosion forges new elements, scatters them, and from those scattered pieces planets and life eventually emerge. The chain from starlight to life is written in every atom, and the link in that chain is the supernova. Next time you hear the word supernova, do not just think of an explosion, think of a recipe that requires patience, time and pressure, but ends in a sudden dramatic flourish. It is the universe's way of seasoning itself, scattering flavour into the bland broth of hydrogen and helium. Without it, the cosmos would be simple, empty and lifeless. With it, the universe becomes rich, complex and alive. Every bright star you see tonight may one day meet this fate. Some will burn quietly and fade, but the most massive will end in fire, scattering their gifts across the galaxy. Their deaths will not be in vain, for their ashes will become the seeds of new worlds, and their elements will find their way into lungs, oceans, and mines. Supernovae are explosions, yes, but they are also acts of creation, writing the next chapters of the universe with every burst of light. Gold and platinum shimmer with a beauty that feels timeless. For millennia, humans have mined them, shaped them into jewellery, stored them as wealth, and admired their glow. Their allure is undeniable, but their true story stretches far beyond human history. To hold a piece of gold in your hand is to hold a fragment of the most violent and exotic events the universe has to offer. These metals, along with other rare treasures such as uranium and thorium, are born not in the gentle fusion of ordinary stars, but in extraordinary cosmic cataclysms where the laws of physics are pushed to their limits. The ordinary cooking of stars, the kind that steadily transforms hydrogen into helium and then into heavier elements up to iron, cannot account for gold and platinum. Fusion stops cold at iron because it no longer yields energy. To go beyond requires something else entirely. A sudden flood of neutrons cramming into nuclei at such speed that new elements can be built before the unstable atoms fall apart. This process is called rapid neutron capture, or the R process. It is not a daily occurrence, nor even a common one. It demands conditions of unimaginable energy and density, and for a long time, astronomers puzzled over where such environments could exist. Supernovae seemed like a likely answer. The collapse of a massive star does unleash a torrent of energy, and for years scientists believed that might be enough to explain the abundance of heavy elements. Yet the numbers did not quite add up. Supernovae could account for some heavy elements, but not the vast richness of gold, platinum, and other R-process treasures we find scattered across the cosmos. The mystery lingered until astronomers turned their eyes towards something even rarer and more dramatic: the collision of neutron stars. Neutron stars are among the strangest objects in existence. They are the remnants of massive stars that exploded as supernovae, their cores compressed into balls only about 20 kilometers across, yet so dense that a teaspoon of their matter would outweigh mountains. Inside them, matter exists in forms that defy ordinary understanding, with neutrons packed shoulder to shoulder in a way they never would be elsewhere. When two of these cosmic titans orbit each other, they spiral closer over millions of years, radiating gravitational waves that ripple through space-time itself. Eventually they collide, and in that moment, the universe produces conditions perfect for the R process. The merger of neutron stars creates what astronomers call a kilonova. In terms of brightness, it rivals a supernova, but its signature light reveals something special. As the stars collide, matter is flung outward at enormous speeds, bathed in neutron-rich environments. Within fractions of a second, atomic nuclei capture neutrons again and again, building up into heavy elements. Gold, platinum, and rare earth metals pour into existence, synthesized in quantities that dwarf anything humanity has ever dug out of the ground. In a single neutron-star collision, enough gold can be created to outweigh Earth. In 2017, astronomers witnessed such an event for the first time. Gravitational wave detectors picked up the ripples from two neutron stars merging, and telescopes around the world turned to watch. They saw a brilliant kilonova flare, and in its light the fingerprints of freshly forged heavy elements. It was the cosmic proof long sought. The treasures we value so highly were born in some of the rarest events in the universe. The rarity of these events is part of what makes the metal so precious. Neutron star mergers do not happen often. In a galaxy like the Milky Way, one might occur only once every 100,000 years, yet each collision seeds vast regions of space with riches. Over billions of years, the heavy elements spread, incorporated into clouds of gas and dust, and eventually into planets. Earth's veins of gold and platinum, the tiny flecks in riverbeds, and the ores buried deep underground all trace back to these ancient and distant collisions. Gold itself is remarkable not only for its rarity, but also for its properties. It does not rust, it does not tarnish, and it is easy to shape. That is why humans, upon discovering it, quickly gave it symbolic meaning. Wealth, power, eternity. Platinum too is resilient, resisting corrosion and withstanding heat, making it useful in modern technology as well as ornament. But their cosmic story gives them a deeper meaning still. They are not just decorative or practical, they are messengers from violent events that shaped the universe. To wear a gold ring is to wear the memory of a neutron star collision that occurred billions of years ago, long before the Earth was born. Other heavy elements share this story. Uranium and thorium, used as fuels in nuclear reactors, were also created in R process events. Their slow radioactive decay acts as a kind of planetary heater, keeping Earth's interior warm and driving plate tectonics. Even the shimmer of rare earth metals used in smartphones and green technologies originates in the same cosmic foundries. Our modern world, from wedding jewellery to renewable energy, is linked to the cataclysmic merging of stars in distant galaxies. It is striking to consider just how far these atoms have travelled. Born in collisions so bright they could briefly outshine entire galaxies, they scattered across interstellar space, drifting for eons. Eventually they became part of the cloud of gas and dust that collapsed to form our solar system. Some sank deep into Earth's crust, where humans would one day mine them. Others became part of the chemistry of our bodies in trace amounts, silently connecting us to the grandest of cosmic events. The human fascination with gold and other rare metals may be rooted in more than their shine. Perhaps part of the allure is that, unconsciously, we sense their rarity, their ancient and cosmic origin. When ancient civilizations buried kings with golden treasures, or when modern couples exchange rings, they are participating in a tradition older than humanity itself, the honouring of matter that was born in the universe's most extraordinary moments. Whenever you next see gold glittering in sunlight or platinum gleaming in a setting of jewels, pause for a moment. You're looking not just at wealth, not just at adornment, but at a piece of cosmic history. That metal was born in violence beyond imagination, in the crushing embrace of neutron stars. It crossed the gulf of space, settled into a planet, and waited patiently for billions of years until hands pulled it from the ground. What seems like a simple ornament is in truth a treasure with a pedigree older than Earth itself. The universe is full of wonders, but few stories are as humbling as this one. The rarest and most precious metals are not made in abundance because their recipe is too demanding, requiring conditions that only exist in fleeting cosmic moments. Their scarcity is not artificial, it is woven into the fabric of the cosmos. They are quite literally treasures of the stars carried across space and time to rest in our world. And when you hold them, you hold not only beauty but the echoes of neutron stars colliding, the fireworks of kilonovae, and the deep, mysterious processes that make the universe both violent and generous. When a star ends its life, it does not vanish quietly. Even in its death, it leaves behind a legacy that drifts onward, carried across the galaxy like ash on a breeze. These ashes are not lifeless dust, but the very building blocks of future worlds. Every explosion, every gentle shedding of a star's layers becomes part of a grand recycling system. Out of stellar remnants, new stars ignite, new planets form, and new stories begin. To follow Stardust in motion is to trace the long journey of matter as it drifts through space, gathering and regathering until it finds itself in oceans, mountains, and even in you. The process begins when stars shed their outer layers. For smaller stars like our Sun, this happens gracefully. As they grow old, they puff out great shells of gas, forming luminous clouds known as planetary nebulae. These shells are rich with carbon, oxygen, and nitrogen, elements cooked during the star's long life. Larger stars die far more dramatically, hurling their contents outward in colossal supernova explosions. In either case, what was once trapped in the fiery core is now free to wander the galaxy. This expelled material becomes dust and gas scattered through the interstellar medium, the vast space between stars. To the human eye, interstellar space might seem empty, but it is anything but. It is filled with particles, atoms, molecules, and grains of dust drifting slowly, spread across immense distances. The density is astonishingly low, like a handful of atoms in every cubic centimetre, yet on galactic scales it adds up to enormous reservoirs of matter. Stardust is not uniform. Some grains are rich in silicates, others in carbon compounds, and still others in heavier elements forged in supernovae. These tiny fragments carry with them the fingerprints of the stars that created them. Scientists have even found microscopic grains of stardust inside meteorites on Earth, their isotopic compositions revealing that they formed around other stars before our solar system even existed. To hold such a grain is to hold a time capsule billions of years older than Earth itself. As this material drifts, it does not stay scattered forever. Gravity, the same quiet force that gathers stars and galaxies, begins to pull dust and gas together. In some regions, shock waves from supernovae compress clouds of matter, nudging them into denser clumps. In others, collisions between galaxies stir the gas, creating fertile grounds for star formation. Wherever the conditions are right, nebulae form. Vast clouds where stardust gathers, thick enough to block light and glow with hidden energy. These nebulae are the true nurseries of the cosmos. Within them, dense pockets of gas and dust collapse under gravity's pull, spinning into disks that eventually form new stars. Around these young stars, leftover material swirls, collides, and sticks together, forming planets, moons, and asteroids. Every rock and river, every drop of water, every living creature begins in the quiet settling of stardust inside a nebula. Consider for a moment the water flowing in rivers or stored in glaciers. The hydrogen in those molecules has existed since the Big Bang, but the oxygen was born in stars. Long ago, a star released its oxygen into space, and those atoms drifted, waiting until they became part of Earth. The same is true for iron in the planet's core, silicon in its crust, and calcium in your bones. Each element took its own winding path, but all shared a journey through interstellar space as dust and gas, carried by the currents of the galaxy. What makes this story so beautiful is the patience involved. The recycling of stardust is not quick. Clouds of gas can drift for millions of years before gathering. Nebulae may persist for tens of millions more before collapsing into new stars, and once a solar system forms, it may take billions of years before life emerges. Yet none of it would be possible without the constant motion of dust between stars, drifting like pollen in a cosmic spring. Astronomers often capture images of nebulae glowing in vivid colours. The red of hydrogen, the green of oxygen, the blue of helium, all reveal the chemical richness seeded by older stars. These images are more than just beautiful photographs. They are snapshots of matter in transition, showing the ashes of one generation becoming the seeds of the next. It is a reminder that even in death stars are generous, giving their remains to build the future. Our own solar system was born from such a nebula. Roughly 4.5 billion years ago, a cloud of gas and dust collapsed, possibly triggered by a nearby supernova. In the centre, the sun ignited, while around it a disk of dust swirled. From that disk, Earth and the other planets took shape. Some of the stardust became comets and asteroids, frozen remnants of the early solar system. Others fused into rocky worlds or gaseous giants. The planets we know today are the children of ancient stardust gathered into new form. Even now the process continues. Dust constantly moves through the Milky Way, forming new nebulae, new stars and new planets. Some of this dust even falls onto Earth every day. Tiny grains drift through the atmosphere, remnants of long-dead stars settling silently on rooftops, oceans and deserts. You may not see them, but with every breath, every step, you share the planet with these invisible visitors from the depths of space. There is something almost poetic in this endless cycle. Stars live, die, and scatter their contents. Dust drifts, gathers, and forms new stars. Planets arise, life emerges, and eventually that life reflects on its own origins. The atoms in your body have been part of this dance for billions of years, moving from star to space to planet to person. Stardust in motion is not just a cosmic phenomenon, it is your story as much as the story of galaxies. Perhaps this is why the night sky feels so familiar, even though it stretches far beyond comprehension. On some level, we recognize ourselves in it. The glow of stars is not just distant light, it is family light, made of the same atoms that shape us. The dust between stars is not foreign, it is the same dust that makes mountains and muscles. We are not merely watching the universe from the outside, we are participating in its ongoing cycle, carried along by the quiet motion of stardust that never truly stops. So when you see an image of a nebula, or when you look up at the stars, remember the journey of those atoms. They have travelled farther than any human ever will, crossing light years of empty space, waiting for their next role. They may one day form part of a star or a planet or even a living creature. Stardust drifts endlessly, but it always finds a home. And that simple truth is one of the universe's most generous gifts. 4.5 billion years ago, our planet began its story not as a solid world, but as a swirl of dust and gas orbiting a young sun. The ingredients were already ancient, forged in long-dead stars and scattered into space by supernovae. Earth is not made from anything new. It is a collector of hand-me-downs, a patchwork quilt sewn from the ashes of countless stellar lives. Iron, silicon, oxygen, carbon, and dozens of other elements gathered in the solar nebula, pulled together by gravity, and eventually formed the planet we now call home. To understand Earth is to understand that it is a cosmic inheritance, a gift from the stars. At the heart of the planet lies iron. During Earth's formation, the young world was a molten sphere, constantly battered by collisions with asteroids and planetesimals. In that liquid chaos, heavier elements sank toward the centre while lighter ones floated upward. Iron and nickel, both born in the cores of massive stars and hurled outward by supernova, collected at the deepest levels. There they formed the dense metallic core that still beats like a hidden heart at the planet's centre. This core is not just a lump of metal, it is dynamic, churning and spinning. Its movement generates Earth's magnetic field, an invisible shield that deflects harmful solar radiation and helps preserve our atmosphere. Without that magnetic protection, life on Earth would face far harsher conditions and perhaps might never have emerged at all. Surrounding this metallic heart is the mantle, rich in silicate minerals. Silicon, oxygen, magnesium, and other elements, themselves products of stellar fusion, joined to create a rocky layer that extends for thousands of kilometers. From this mantle came volcanic eruptions, mountain ranges, and the slow drift of continents. The silicate crust that eventually cooled on top became the solid surface beneath our feet. When you hold a rock, you are holding the condensed dust of stars, arranged into minerals by the patient cooling of the Earth's surface. Granite cliffs, sandy deserts, and crystal formations all owe their existence to the inheritance of silicon and oxygen from ancient stars. Above the crust, the atmosphere took shape. At first, it was hardly the breathable air we know today. Early Earth's atmosphere was thick with carbon dioxide, methane, ammonia, and water vapour. The oxygen that now fills every breath was absent, but the elements were there, waiting for life to transform them. Oxygen from stellar furnaces was locked in rocks and minerals, and hydrogen from the Big Bang swirled in abundance. When early microbes discovered how to split water and release oxygen, the air slowly filled with the element that now sustains every animal on the planet. Even nitrogen, which makes up most of the atmosphere today, is a stellar gift. Born in massive stars and scattered in supernova, it drifted into Earth's atmosphere, becoming the quiet, invisible backdrop for life. And then there are the oceans. Water is one of Earth's most extraordinary features, and its origins tell a story that spans billions of years. The hydrogen came directly from the birth of the universe, the simplest atom and the oldest. The oxygen came from stars, flung into space and eventually bound to hydrogen in the simplest, yet most transformative chemical union. Some of this water may have formed on Earth as the young planet cooled, while some may have been delivered by icy comets and asteroids that bombarded the surface. Either way, the oceans are a blend of cosmic legacies. Each wave carries atoms that once drifted through interstellar space, waiting for the right planet to call home. Earth's inheritance extends beyond its obvious layers. Trace elements scattered throughout the crust tell stories of stellar origins. Calcium, crucial for bones and shells, came from stars that burned helium into heavier elements. Potassium and sodium, essential for nerve signals and muscle contractions, arrived from similar stellar processes. Even rarer elements, like gold and uranium, arrived from neutron star collisions, making their way into Earth's crust where humans would later discover and use them. To live on this planet is to live surrounded by cosmic heirlooms, each with its own story of creation. What makes Earth remarkable is not just the ingredients it inherited, but how they combined. Other planets in the solar system received similar gifts, but the balance here was special. The iron core provided protection, the silicate crust offered stability, the atmosphere transformed under the influence of life, and the oceans created a solvent for chemistry. The recipe was perfect not by design, but by the unfolding of physical laws, a series of cosmic accidents that came together into something stable and fertile. Even the violent parts of Earth's past played roles in shaping its inheritance. Giant impacts, such as the collision thought to have created the Moon, redistributed elements and altered the planet's chemistry. Volcanic eruptions released gases that helped build the atmosphere. Plate tectonics recycled minerals, keeping the crust dynamic rather than stagnant. The story of Earth is one of constant reworking, with the original stellar ingredients being cooked, mixed, and reshaped into ever-new forms. It is humbling to think that the same iron that forms the core of Earth also flows in your blood, or that the oxygen that fills your lungs once drifted as stardust through space. The inheritance of Earth is not just geological, it is personal. Every living being carries within it the atoms that stars left behind. The calcium in your teeth, the carbon in your muscles, the phosphorus in your DNA. All of it was handed down to you through Earth's patient collecting of stellar remnants. Sometimes when we look up at the night sky, it feels as though the stars are far away, distant lights beyond reach. Yet the truth is that the stars are already here, beneath our feet and within us. Earth is their legacy, their carefully gathered hand-me-downs arranged into a planet that became home. The continents, the atmosphere, the oceans, and the life they sustain are all part of the same inheritance. This view changes how we see the world. A mountain is not just rock but a monument to ancient stars. A river is not just water but the flow of hydrogen from the dawn of time, mixed with oxygen from stellar fire. Even the air is not just empty space, but a mixture of elements borrowed from across the galaxy. To live on Earth is to live in the midst of a vast family story, one that stretches back to the birth and death of stars. In the end, Earth's elemental inheritance is not a simple list of components, but a reminder of connection. Every part of our world is tied to events that happened billions of years ago, in places unimaginably distant. The iron at Earth's centre, the silicon in its crust, the oxygen in its air and the water in its seas all began as stardust, set in motion by forces far larger than ourselves. And yet, here they are, gathered together into a planet where life breathes, grows and wonders at its own origins. So when you stand barefoot on the ground, or drink a glass of water, or take a deep breath, pause for a moment. You're experiencing the legacy of stars, the inheritance passed down through fire and dust. Earth is not just a planet. It is the heir to the cosmos, carrying within it the gifts of countless stellar lives, assembled into a home for life to flourish. Water is one of those substances so familiar that it is easy to forget how strange and miraculous it really is. It pours from clouds as rain, it rushes through rivers, it freezes into ice, and it steams into vapour. It covers most of our planet's surface and makes up a large portion of our own bodies. We drink it, cook with it, swim in it, and breathe it out with every exhalation. Yet beneath this ordinariness lies a cosmic story that begins not on Earth, but in the hearts of stars. Water is not just a planetary feature. It is a union of stellar elements, a liquid thread that connects life to the wider universe. At its simplest, water is a marriage between hydrogen and oxygen. Hydrogen is the oldest of all elements, created in abundance in the first few minutes after the Big Bang. It is the lightest atom possible, a single proton with an electron in tow, and it has been drifting through the cosmos since time began. Oxygen, on the other hand, is a relative latecomer. It formed much later, inside stars that had already lived long lives, burning helium and carbon until the conditions were right to create oxygen nuclei. When those stars died, they cast their oxygen into space, mixing it with the hydrogen that had been there all along. Out of that meeting came water, not in the form of raindrops or oceans at first, but as molecules floating quietly through interstellar space. What makes water remarkable is not just its availability, but its properties. It behaves in ways that seem almost tailor-made for life. For instance, water is an extraordinary solvent, able to dissolve more substances than any other liquid. This is why it is called the universal solvent. In the chemistry of life, that ability is indispensable. Sugars, salts, amino acids, and countless other molecules all dissolve in water, allowing them to mix and interact in ways that make metabolism possible. Without water, the chemistry of life would stall before it could even begin. Water is also unusual in how it responds to temperature. Most substances become denser as they freeze, but water does the opposite. Ice floats because it is less dense than liquid water, a property that has saved countless ecosystems. In cold winters, lakes and ponds freeze on the surface while liquid water remains below, allowing fish and plants to survive until spring. If water behaved like most substances, freezing solid from the bottom up, life in cold climates would struggle to endure. This quirk is no accident, but a result of the unique angle at which hydrogen and oxygen bond, giving water molecules a bent shape that locks into an open crystalline structure when frozen. Another wonder of water is its high heat capacity. It takes an unusual amount of energy to warm it up or cool it down. This means that oceans act as thermal regulators for the planet, smoothing out wild temperature swings and making Earth habitable. Imagine a world without this balancing effect. Days scorching, nights freezing, and climates far less stable. The gentle moderation of water has allowed life to evolve in relative comfort, shielded from extremes that might have made survival impossible. The origins of Earth's water are still debated, and the truth may be a blend of several sources, some of it likely condensed from hydrogen and oxygen already present in the protoplanetary disk that formed the solar system. Some may have been delivered later by comets and asteroids, icy messengers that bombarded the young Earth. Whichever the case, the point is clear. Water is not a purely local phenomenon. It is the cosmic product of two elements with very different histories, brought together through the workings of gravity and chemistry. And water is not unique to Earth. Astronomers have detected water molecules in the atmospheres of distant exoplanets, in the icy plumes erupting from moons like Enceladus and Europa, and even in the gas clouds between stars. It seems that wherever hydrogen and oxygen exist in abundance, water is bound to appear. Its presence throughout the cosmos suggests that the conditions for life may be more common than we once thought. If water flows elsewhere, perhaps the chemistry of life flows with it. On Earth, water is not only abundant but deeply integrated into every process of life. It flows through our veins, carrying nutrients and waste. It shapes the landscapes, carving valleys and deltas. It cycles endlessly between sky, land, and sea, evaporating into clouds, condensing into rain, seeping into soil and returning again. Every drop of water has been used and reused countless times, circulating through organisms, rocks, and air for billions of years. The glass you drink from may hold molecules that once froze in glaciers, once swirled in the belly of a dinosaur, or once drifted as vapor above an ancient sea. There is also poetry in how water links us to the stars. Hydrogen, born in the very first minutes of the universe, and oxygen, forged in stellar furnaces, come together to create the most vital liquid for life. Every sip you take is a direct connection to both the dawn of time and the deaths of stars. It is a bridge across cosmic history poured into a cup. Consider too how water has shaped human civilization. Rivers provided routes for travel and trade, fertile ground for agriculture, and the power to turn mills and machines. Oceans connected continents, spreading cultures and ideas. Even today, access to water defines where people live and how they thrive. Our reliance on it is total, not only biologically, but socially and culturally. And behind it all lies the cosmic accident that hydrogen and oxygen, with their stellar origins, happen to bond so perfectly. Water also plays a central role in the search for life beyond Earth. Astronomers often summarize the quest with a simple phrase, "Follow the water." Wherever water exists in liquid form, the possibility of life seems stronger. That is why Mars, with its signs of ancient rivers and lakes, continues to fascinate. It is why moons with hidden oceans beneath icy shells are so closely studied. If life is to arise elsewhere, it will likely do so where water provides the solvent for chemistry. In all of this, one truth stands out. Water is not ordinary. It is as extraordinary as gold or diamonds, not because it is rare, but because it is perfectly suited for the role it plays. The very qualities that make it common also make it indispensable. It dissolves, it stabilizes, it flows. It turns two of the universe's most abundant elements into something far greater than the sum of its parts. The next time you pour a glass of water, pause for a moment to think about what you are holding. The hydrogen has been around since the birth of the cosmos. The oxygen was once locked in a star's blazing core, released in its death. And together, after journeys across time and space, they form the liquid that sustains you. What seems like an everyday drink is in truth a taste of the universe's most remarkable chemistry, a solvent that has carried the story of life for billions of years and will continue to do so for billions more. Water is not just a backdrop for life, but the stage upon which the play unfolds. It is the cosmic solvent, the quiet miracle that allows atoms to mingle, molecules to meet, and biology to bloom. Without it, the universe might still be rich in stars and planets, but silent, sterile, and empty of song. With it, Earth became blue, vibrant, and alive. Every person carries within them a quiet cosmic history, written not in words but in atoms. When people say we are made of stardust, it is not a metaphor or poetic exaggeration. It is a literal truth. The elements that make up the human body were forged in stars scattered into space and gathered into the chemistry of life. From the calcium strengthening your bones to the iron flowing in your blood, every atom tells a story billions of years old. To look in a mirror is, in a very real sense, to see a fragment of the universe reflecting upon itself. Consider carbon, the scaffolding of biology. Every cell in your body is built on carbon's versatile frameworks. Carbon atoms form the backbone of DNA, the spiral staircase of heredity, and they knit together the proteins that do the work of life. They assemble into sugars that fuel cells and into fats that store energy for later. Carbon's unique ability to bond in 4 directions allows for an almost infinite variety of molecular structures. Yet none of this would exist without the triple alpha process in long-dead stars, where 3 helium nuclei collided under immense heat and pressure to form carbon. The carbon in your body was once the ash of a dying star, drifting through space before finding its way into Earth and eventually into you. Next, think of oxygen, the element of breath. Every inhale fills your lungs with oxygen molecules, which slip into your blood and hitch a ride to your tissues. There, oxygen helps burn sugars, releasing the energy that keeps you alive. Oxygen is the second most abundant element in the human body, woven into water, proteins, fats, and DNA. Its origin lies in the fusion furnaces of stars more massive than the Sun, where carbon nuclei captured helium to form oxygen. When those stars died, they spilled their oxygen into space, enriching the galaxy. Some of those atoms became part of Earth's oceans and atmosphere. Others became part of you, joining with hydrogen in the water that flows through your veins and in the oxygen you exhale with every breath. Iron gives the human story an especially dramatic link to the cosmos. In your blood, iron atoms sit at the heart of hemoglobin, the molecule that carries oxygen from your lungs to every cell. Each hemoglobin molecule contains iron at its centre, like a clasp that holds oxygen in place. Without iron, your body would suffocate despite having lungs full of air. Iron, however, is not created in the steady fusion of stars. It marks the end of the fusion chain, the cosmic full stop. To make it in abundance requires catastrophe, the collapse and explosion of massive stars. In a supernova, shock waves forge iron in titanic amounts and hurl it across the galaxy. The iron in your blood was once caught in such an explosion, a relic of a star's final moments. Every beat of your heart is powered by the ashes of stellar death. Calcium, the element that fortifies your bones and teeth, tells another chapter of this story. Calcium is made when massive stars fuse lighter elements in their shells during their final stages of life. Like iron, it is released in the chaos of supernovae, carried outward into the galaxy and mixed into the dust clouds that form new worlds. On Earth, calcium gathered into limestone shells and the skeletons of creatures. In humans, it hardened into bone, creating the framework that lets you stand, walk, and dance. The strength of your skeleton is, at its core, the strength of stars long gone. Phosphorus is less abundant but just as essential. It forms part of DNA, linking the rungs of the genetic ladder and it helps store energy in the molecule ATP, the cell's rechargeable battery. Phosphorus originates in massive stars and is scattered by supernovae. Without it, life as we know it could not organise or reproduce. Even the sparks of thought rely on phosphorus, because the energy currency of neurons depends on it. Every idea you have ever had has been paid for with a tiny piece of a star. Potassium and sodium too deserve their mention. These elements, also born in stars, are central to nerve impulses. Every signal that flashes along your nervous system, from the twitch of a muscle to the rhythm of your heartbeat, depends on the careful balance of potassium and sodium across cell membranes. When you think, when you laugh, when you dream, you're using elements forged in stars to send tiny electrical whispers through your body. The conversation of your nervous system is in a sense a conversation of stardust. Even trace elements carry cosmic stories. Zinc supports enzymes, copper helps blood clot, iodine regulates hormones, and magnesium assists in countless reactions. Each was born in different stellar processes, some in ordinary fusion, others in the intense neutron storms of supernovae or neutron star collisions. They are present in your body only in small amounts, but without them, the machinery of life would grind to a halt. Even the tiniest portions of your biology are echoes of celestial processes. What is striking is how well suited these elements are for life. Carbon provides endless structures, oxygen fuels reactions, iron carries oxygen, calcium builds bones, phosphorus stores energy, and potassium sparks signals. Life did not invent these properties, it used what the universe had provided. Biology is, in a way, the clever repurposing of stardust. This inheritance also creates a sense of kinship. You share elements not only with other people, but with all living things. The calcium in your bones is the same calcium in the shells of clams. The iron in your blood is the same iron in the core of Earth. The oxygen you breathe is the same oxygen that lights fires and corrodes metal. We are all variations on the same theme, arranged differently but made of the same cosmic palette. It is easy to feel small when thinking about the size of the universe, but this story offers another perspective. You are not separate from the cosmos, looking at it from a distance. You are of it, composed of its elements, carrying its history in every atom. Stars exploded billions of years ago, and those explosions made your life possible. Every heartbeat is powered by that legacy, every step grounded in elements handed down across eons. On the next occasion you feel the steady rhythm of your pulse, or take a deep breath, remember the cosmic origin of what sustains you. The oxygen in your lungs, the iron in your blood, the calcium in your bones, the carbon in your cells. All of it has travelled across space and time to be here now. You're not just alive, you're a living mosaic of stellar remnants, a collection of atoms that once glowed in the hearts of suns. The stardust in your body is not metaphorical but literal, and it tells you something profound. You are the universe, thinking and breathing, remembering its own story. For most of human history, the stars were silent. They shone in the night sky as lights beyond reach, inspiring myths, guiding travellers, and serving as cosmic markers of time. But what they were made of, and whether they shared anything in common with the world below, remained a mystery. People gazed upward, wondering if the heavens were composed of some divine substance, entirely different from earthly matter. The idea that the same elements found in firewood and rivers might also be present in the sun and distant stars would have seemed absurd to many. And yet, the long detective story of Starlight slowly revealed exactly that truth. The earliest seekers of knowledge began not with science as we know it, but with alchemy. For centuries, alchemists across cultures pursued the dream of transforming base metals into gold, chasing immortality through elixirs and hidden formulas. Though their goals were often fantastical, their work was not entirely fruitless. Alchemists experimented with matter, recorded observations, and laid the foundations of chemistry. What they lacked was a clear understanding of elements themselves. To them, matter was shaped by mysterious principles, the four classical elements of fire, water, air, and earth, rather than the atomic building blocks we recognise today. The shift began with the scientific revolution. In the 17th century, Robert Boyle challenged the old Aristotelian view of matter. His work, The Skeptical Chymist, argued that substances could be broken down into more fundamental components, which he called elements. Soon after, Antoine Lavoisier brought clarity to the idea by carefully weighing substances before and after chemical reactions. He showed that matter was conserved and began to compile a systematic list of elements. For the first time, chemistry had a sturdy foundation, and the world's ingredients were becoming catalogued. But there was still a problem. This understanding was based on what could be tested in laboratories on Earth. The stars were distant, untouchable. How could anyone hope to know their composition? They could not be bottled or weighed, and no one could travel to them. To uncover their secrets, humanity needed a new tool, one that could translate the light of stars into a language we could read. That tool turned out to be spectroscopy. The principle of spectroscopy is simple yet profound. When elements are heated, they emit or absorb light at very specific wavelengths. Each element leaves a unique pattern, a fingerprint of lines that can be seen when light is passed through a prism or diffraction grating. This discovery was made in the early 19th century, when scientists like Joseph von Fraunhofer noticed dark lines crossing the spectrum of sunlight. These Fraunhofer lines, as they became known, hinted that something in the sun was absorbing specific colours of light. But what? The answer came a few decades later when Gustav Kirchhoff and Robert Bunsen realised that each element produced its own spectral signature. Sodium, for instance, created a pair of bright yellow lines. Hydrogen gave off distinctive red and blue-green lines. By matching these laboratory spectra with the dark lines in the sun's light, they cracked the code. The sun contained the same elements as Earth. The heavens and the Earth were made of the same stuff, and this was a revolutionary moment. The ancient divide between celestial and terrestrial matter collapsed. The stars were no longer made of mysterious quintessence, but of atoms familiar to chemists. Suddenly, the periodic table was not just a catalogue of earthly matter, but a universal ledger. Every element, from hydrogen to uranium, had its place not only in laboratories, but also in the cosmos. Spectroscopy also gave rise to astonishing discoveries. In 1868, astronomers observing a solar eclipse detected a spectral line that did not match any known element. They named the mystery substance helium, after Helios, the Greek god of the sun. Only later was helium found on Earth, first in volcanic gases. This was the first element discovered in the sky before it was found on our planet, a reversal of the usual order of knowledge. It was a reminder that the universe still held surprises, waiting to be decoded by light. Through the 20th century, spectroscopy continued to deepen our understanding. Cecilia Payne, a young astronomer in the 1920s, analysed stellar spectra and concluded that hydrogen was by far the most abundant element in the universe, followed by helium. Her findings overturned the assumption that stars were composed mainly of heavier elements like Earth. At first, her results were dismissed by established astronomers, but in time, they were recognised as one of the most important insights in astrophysics. Payne's work revealed that stars were not only suns, but also furnaces dominated by hydrogen, patiently forging heavier elements. This recognition opened the door to the next great leap, understanding nucleosynthesis, the creation of elements within stars. In the 1950s, a landmark paper by scientists including Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, often abbreviated as B²FH, outlined how different elements were formed in stars through fusion, supernovae, and neutron capture. It was the missing piece that tied the periodic table to cosmic processes. The detective story of Starlight had reached its climax. The very atoms in our bodies had been traced back to stellar origins. It is hard to overstate the beauty of this revelation. For millennia, people had gazed at stars and woven myths, imagining gods, animals, and heroes in the constellations. The truth turned out to be no less wondrous. The stars were not distant, untouchable mysteries, but our ancestors in a chemical sense. They lived, they burned, they died, and in doing so, they seeded the universe with the elements of life. The story of discovery did not stop there. With modern telescopes, astronomers now analyze spectra from galaxies billions of light years away, reading the elemental composition of the universe across time. They have mapped how the abundance of elements has changed as generations of stars lived and died. The cosmic recipe, once hidden in silence, is now visible as a story unfolding across billions of years. Even today, spectroscopy continues to be the astronomer's detective kit. It is how exoplanet atmospheres are studied, how the birthplaces of stars are examined, and how distant galaxies are understood. Every line in a spectrum is a clue, every shift in colour a whisper from matter across the void. With each discovery, the connection between earth and sky grows clearer. There is a quiet poetry in the fact that light, something that travels across vast distances, can carry so much information. The sun is 150 million kilometres away, and yet, by splitting its light, we can learn its composition as if it were in a laboratory flask. Light from distant stars travels for centuries or millennia before entering a telescope, and when it does, it carries with it the secrets of its origin. The universe leaves fingerprints everywhere. We only had to learn how to see them. The journey from alchemy to spectroscopy shows the power of curiosity. What began as attempts to transmute metals into gold ended with the revelation that the elements themselves are universal, created in the furnaces of stars. The myths of fire, water, air, and earth gave way to the reality of hydrogen, helium, carbon, and oxygen, and the recognition that these atoms are not only the ingredients of Earth, but of the stars above. Come the next time you look at the night sky, remember that it is not just a spectacle of light. It is also a message. Every star beams out its identity. Every photon carries the story of the elements within. Humans learn to read that message, and in doing so, discovered their own place in the cosmos. What once seemed distant and divine turned out to be deeply familiar. The heavens and the earth are one, written in the same language of atoms, revealed by the detective work of Starlight. The universe is not wasteful. Matter, once created, is never truly lost. Instead, it cycles endlessly, passing from one form to another, from stars to space and back again. This is the great act of cosmic recycling, a process that has been unfolding for billions of years. It is the reason galaxies sparkle with new stars, the reason planets form from dust, and the reason life exists at all. Without this perpetual reuse of stellar material, the cosmos would be static and sterile. Instead, it is dynamic, renewing itself with every generation of stars. At the beginning, things were much simpler. Hydrogen and helium dominated the young universe, with only a trace of lithium. These were the first raw materials, drifting in vast clouds. Gravity gathered them into stars, and inside those stars new elements were forged. When the stars grew old, they released their enriched contents, scattering them into the galaxy. Those scattered elements joined new clouds, which collapsed into new stars, and the cycle began again. Every atom in your body has been through this cycle at least once, and perhaps many times, before arriving at its current role. Galaxies are the stage where this recycling plays out. Within them, stars are born in nurseries of gas and dust called nebulae. Some of these nurseries glow brightly, lit by the energy of young stars within them. Others are dark, their dust so thick that light cannot pass through. These regions are rich in molecular clouds, dense with hydrogen molecules, carbon compounds, and grains of silicates. Out of these raw ingredients, gravity sculpts new stars. As stars ignite, they sweep their surroundings with winds of radiation, sculpting the clouds and sending shock waves that trigger further star formation. Already the recycling process is at work, with one generation of stars helping to shape the next. The lives of stars vary greatly, depending on their mass. Some live for trillions of years, burning their hydrogen slowly and steadily. Others, far more massive, blaze through their fuel in only a few million years, ending in spectacular explosions. Regardless of the details, all stars eventually return material to the galaxy. Smaller stars shed their outer layers, forming planetary nebulae that drift outward. Larger stars explode as supernovae, scattering heavy elements across space. Even the remnants, white dwarfs, neutron stars or black holes, play their part by influencing their surroundings, tugging on nearby matter and shaping galactic dynamics. Every generation of stars adds something new to the cosmic pantry. The first stars could only burn hydrogen and helium, creating heavier elements like carbon and oxygen. Later generations inherited those elements, using them to forge even heavier ones like silicon, iron and beyond. By the time our solar system formed, countless cycles had already taken place, enriching the gas cloud with a diversity of atoms. This is why Earth is not a barren world of hydrogen and helium, but a complex planet filled with oceans, continents and life. Recycling is not limited to stars alone. Galaxies themselves breathe in and out. Powerful stellar winds and supernova explosions push gas outward, sometimes ejecting it from the galaxy entirely. Yet over time, gravity draws much of it back, allowing new waves of star formation. Even galaxy collisions play a role. When galaxies merge, their gas clouds collide and compress, triggering bursts of starbirth. The Milky Way and the Andromeda Galaxy, destined to collide in a few billion years, will one day fuse their matter together, creating a new galaxy enriched with the remnants of both. This endless reworking of matter creates a sense of continuity. The oxygen in your lungs may once have been part of a star that lived and died long before the sun was born. The calcium in your bones may have drifted through interstellar space for billions of years before finding a home on Earth. The iron in your blood may have been forged in a supernova that exploded in a distant corner of the galaxy. Each element has been reused again and again, part of different stars, different worlds, and now part of you. Even dust plays a role in this cycle. Interstellar dust grains, often no larger than smoke particles, are coated with ices of water, ammonia, and carbon monoxide. These grains clump together, sticking like tiny seeds of matter. Over millions of years they grow into larger clumps that eventually become planetesimals, the building blocks of planets. The dust between stars is not wasted debris, but the raw material for future solar systems. When you wipe dust from a windowsill, you're performing a small-scale version of the same process that galaxies carry out, transforming tiny grains into something far greater. What makes cosmic recycling so captivating is that it is both violent and delicate. Supernovae tear stars apart with unimaginable force, yet the ashes drift gently through the galaxy, like pollen waiting for new soil. Black holes consume matter with insatiable hunger, yet the jets they fire into space may help regulate star formation in their host galaxies. Collisions and chaos feed the balance, ensuring that matter is never idle for long. It is a cycle written in destruction and renewal, both endless and necessary. Life itself depends on this recycling. Without repeated generations of stars, there would be no carbon, oxygen, or nitrogen for biology to use. Without supernovae, there would be no calcium for bones, no phosphorus for DNA, no iron for blood. Without water-rich asteroids and comets, Earth might never have gained its oceans. Everything we consider ordinary is in fact the product of countless cosmic hand-me-downs. Life is not a separate phenomenon, but a late chapter in a story that began with hydrogen atoms drifting through space. Astronomers often say that we live in a middle-aged universe. Enough cycles of recycling have occurred to enrich galaxies with heavy elements, but the cosmos is still full of gas and dust for new stars to form. Billions of years from now, star formation will slow, and galaxies will grow quieter as their raw material runs out. But for now, the recycling continues at a steady pace, ensuring that the universe remains vibrant and dynamic. There is something comforting in this cosmic rhythm. Stars live and die, galaxies collide and merge, elements scatter and regather, but nothing is ever truly lost. The atoms that once burned in a star's heart may now shimmer in a crystal, flow in a river, or beat in a pulse. The cycle of recycling ensures that everything is connected, everything is shared, and everything is temporary yet enduring. So when you gaze at the Milky Way stretching across the night sky, remember that it is not a static band of stars. It is a vast ecosystem, constantly recycling, renewing, and reshaping itself. The light you see comes from stars in the midst of their lives, but around them, dust and gas are already preparing for what comes next. The galaxy breathes, the universe renews, and you are part of the cycle. In the great act of cosmic recycling, there is no true ending, only transformation. Time is one of those things we can never hold, yet we are surrounded by its traces. We see it in the rings of a tree trunk, the lines on a face, or the slow crumbling of stone. In the cosmos, time is written not in wood or wrinkles, but in atoms. The very elements forged in stars carry with them clocks that tick invisibly, measuring ages far older than any human calendar. Through radioactive isotopes and the steady rhythm of atomic decay, the universe keeps time, and we have learned to read it. Radioactive decay is the quiet metronome of matter. Certain isotopes, versions of elements with extra neutrons tucked inside their nuclei, are unstable. Over time, they break down into more stable forms, releasing energy and particles in the process. What makes this remarkable is the reliability. Each isotope decays at its own fixed rate, measured by its half-life, the time it takes for half of a sample to transform. Whether deep underground, locked inside a meteorite, or drifting in interstellar space, these isotopes tick away with steady precision. They are nature's built-in clocks, keeping track of eons with calm indifference. Take carbon-14, one of the most famous of these cosmic timekeepers. It is formed in Earth's atmosphere when cosmic rays collide with nitrogen atoms, turning them into radioactive carbon. Plants absorb it through photosynthesis. Animals eat the plants, and so carbon-14 becomes part of every living being. While alive, organisms continually exchange carbon with the environment, keeping the amount of carbon-14 steady. But once life ends, the clock starts. Carbon-14 decays into nitrogen at a predictable pace, and by measuring how much remains, scientists can date fossils, bones, and artifacts up to about 50,000 years old. This method, known as radiocarbon dating, has illuminated human history, from the age of ancient tools to the timeline of lost civilizations. But carbon-14 is only a short-term clock. For the grander timescales of geology and astronomy, we turn to isotopes with far longer half-lives. Uranium-238, for instance, has a half-life of about 4.5 billion years, nearly the age of Earth itself. As uranium decays into lead, the ratio between the two elements changes in a way that reveals the age of rocks. By applying this method to the oldest minerals on Earth, tiny crystals called zircons, scientists have determined that our planet is roughly 4 billion years old, 0.54 billion years old. The same technique applied to meteorites gives similar ages, confirming that the solar system as a whole was born around that time. Thorium, potassium, rubidium, each offers its own clock running at different speeds. By cross-checking them, scientists build a robust timeline of planetary history. These isotopes tell us when volcanoes erupted, when mountains formed, and when ancient rocks solidified. Without them, Earth's story would remain vague, its deep past lost in shadows. With them, we can read the planet's history like a book, each isotope a page number marking where we stand. The same principles extend far beyond Earth. Radioactive isotopes are found throughout the cosmos, and by measuring them, astronomers can estimate the ages of stars and even the universe itself. One striking example comes from uranium and thorium found in ancient stars. By comparing the abundance of these long-lived isotopes to stable elements, scientists can calculate how much time has passed since those atoms were forged in supernovae or neutron star mergers. These stellar clocks suggest ages of around 12 to 13 billion years, giving us a glimpse into the universe's earliest generations of stars. Another powerful tool comes from isotopes of elements like strontium and neodymium, which record the processes that built planets. As Earth differentiated into core, mantle, and crust, these isotopes shifted in ways that reveal the sequence of events. By analysing them, geologists can piece together not only when Earth formed, but how it evolved chemically over time. It is as if the planet carries its birth certificate and diary within its rocks written in isotopic ink. Even light itself can serve as a kind of clock when combined with isotopes. In supernovae, freshly forged radioactive elements like nickel-56 decay into cobalt and then into iron, powering the afterglow of the explosion. By observing the light curve of a supernova and matching it to the decay of these isotopes, astronomers can measure the timing of the event and learn about the processes inside. The brilliance of the cosmos is literally fueled by the ticking of radioactive clocks. The oldest clock of all, however, comes not from isotopes but from the cosmic background radiation, the faint afterglow of the Big Bang. By studying its patterns and combining them with the expansion of the universe, scientists have determined that the cosmos is about 13.8 billion years old. This number is not plucked from thin air, but cross-checked against the ages of the oldest stars and clusters, ensuring that the cosmic timeline remains consistent. What makes radioactive clocks so compelling is that they are utterly impartial. They do not care about human lifespans or civilizations. They tick steadily, marking off millions and billions of years with the same calm rhythm. They remind us that time is vast, and that our own histories are but fleeting moments against the backdrop of cosmic ages. And yet, these clocks are not abstract curiosities. They touch our daily lives. The potassium-40 in your own body, for instance, is mildly radioactive, decaying slowly even as you read these words. It poses no danger, but it is a reminder that the ticking of atomic clocks is not confined to distant stars or ancient rocks. It is happening within you, tying your body to the great cycles of decay and renewal that run throughout the cosmos. There's also a certain poetry in how these clocks reveal continuity. The uranium in a rock, the carbon in a bone, the thorium in a star, all are telling the same story in different chapters. Each isotope is a timepiece set in motion billions of years ago, still running today, still offering us a way to measure what otherwise seems immeasurable. Without them, we would struggle to grasp the scale of cosmic history. With them, we can trace time back almost to the beginning. When you think of time, you might imagine hours on a clock or days on a calendar. But in reality, the deepest measures of time are hidden in matter itself. Every atom has a past, and some carry within them the ability to record it. To hold a piece of ancient zircon, or to look at a distant star's spectrum, is to hold a record of billions of years, written not in ink but in isotopes. When you next wonder about the age of the universe or the antiquity of the earth beneath your feet, remember that the answers are not distant mysteries. They are carried in the atoms around you, quietly keeping time. Radioactive isotopes are the clocks of creation. Their steady ticking a reminder that time itself is etched into matter. And in listening to them, humanity has learned not only how old things are, but how deeply we belong to the long unfolding story of the cosmos. Long before laboratories and telescopes, long before the language of protons and neutrons, humanity looked at the world and tried to make sense of what it was made of. The sky, the seas, the soil, the flames that warmed and destroyed, all of these demanded explanation. Without the tools of modern science, cultures across the world reached for stories, weaving mythologies around the elements they saw and felt every day. Fire, air, water and earth became not just substances, but sacred forces. These early attempts to understand matter were poetic drafts of the same grand story science tells today, a story of ingredients and recipes shaping the universe. Take fire, for example. To ancient peoples, fire was a mystery unlike any other. It seemed alive, consuming wood and releasing smoke, dancing with unpredictable motion. The Greeks saw it as one of the 4 fundamental elements. Heraclitus, the philosopher, even described the cosmos as an ever-living fire, kindling in measures and going out in measures. In his vision, fire was not merely warmth or light, but the eternal principle of change itself. In Zoroastrianism, fire became a sacred symbol, representing truth and purity, tended carefully in temples as a divine presence on earth. In many cultures, fire was linked to the heavens, a gift from the gods, sometimes stolen, as in the Greek myth of Prometheus, who defied Zeus to bring fire to humanity. To imagine fire as an element was both a practical and a spiritual response. It was too powerful, too essential, to be anything less than fundamental. Water inspired equally deep reverence. To early societies, it was both a source of life and a source of fear. Rivers brought fertility to dry land, but floods could erase entire villages. In Egypt, the Nile's yearly flooding became a rhythm of survival, so much so that water entered into their spiritual understanding of the cosmos. The Greeks named one of their primordial deities Oceanus, a great river encircling the world. In Hindu cosmology, all of creation arises from cosmic waters, and in Norse myth, the primeval void Ginnungagap was filled with mist and icy rivers, from which the first giant was born. Water was not just an element, but the womb of existence, the reservoir from which life itself emerged. Air, though invisible, was no less significant. It was breath, wind, spirit, intangible yet essential. In Chinese philosophy, the concept of qi, often translated as breath or energy, infused the world, linking air to life force itself. In Greek thought, air was one of the classical elements associated with balance and the mind. The Hebrew word ruach and the Greek pneuma both mean both wind and spirit, intertwining the physical and the divine. To breathe was to participate in a sacred exchange, inhaling life and exhaling essence. Even without microscopes or chemistry, people intuited that air connected everything, that it flowed not only around us but through us, invisible yet indispensable. Earth, the solid ground beneath our feet, was the most obvious of the elements, and perhaps the most comforting. In many traditions, Earth was the mother, the nourisher, the stable base on which life depended. The Greeks personified Earth as Gaia, the primordial mother who gave birth to mountains and gods. In Andean cultures, Pachamama, Mother Earth, still embodies fertility and abundance. In Hindu cosmology, the goddess Prithvi is Earth itself, sustaining all beings. Soil, stone and mountain were not just physical matter, they were sacred, the eternal foundation of the world. These 4 elements, fire, air, water and earth, became the pillars of countless cosmologies. To the Greek philosopher Empedocles, they were eternal and indestructible, endlessly combining and separating under the influence of love and strife, forces that governed their interactions. To the Chinese, a similar but distinct framework of 5 elements, wood, fire, earth, metal, and water, structured the universe, describing not only material substances but cycles of change in medicine, music, and governance. Across cultures, elements were not only ingredients of matter, but metaphors for the patterns of life itself. What is striking is how closely these mythologies mirror the search for unity that science later pursued. The ancients knew nothing of atoms or fusion, yet they sensed that the diversity of the world must be built from simpler components. To explain rain, growth, storms and decay, they turned to elemental archetypes: fire for energy, water for change, air for movement, Earth for substance. In their simplicity, these categories captured something essential: the idea that beneath the complexity of life lies a small set of fundamental ingredients. Over time, these mythological frameworks gave way to scientific ones. The philosopher Democritus imagined indivisible atoms as the true building blocks of matter, a vision that anticipated discoveries made 2,000 years later. Alchemists, in their quest to transform metals and discover elixirs, kept alive the dream of hidden essences. Slowly, through experiments and measurements, chemistry emerged. The 4 elements of myth faded, replaced by dozens of real elements on the periodic table. Yet the spirit of the search remained the same, a longing to uncover the recipe of the universe. Even today, the echoes of these old elemental systems linger in language and thought. We still speak of someone being grounded like the earth, or of ideas catching fire. We describe emotions as storms, breaths as spirit, rivers as lifeblood. The metaphors of the classical elements continue to shape our imagination, bridging the gap between ancient myth and modern science. Science, of course, has shown that fire is not an element but a process, the rapid oxidation of fuel releasing energy. Water is not elemental but a molecule of hydrogen and oxygen. Air is a mixture of gases, mostly nitrogen and oxygen, with traces of carbon dioxide and argon. Earth is not a single substance but a complex blend of minerals and metals. Yet knowing this does not diminish the wonder. If anything, it deepens it. Fire's dance is the product of oxygen atoms combining. Water's flow is the union of hydrogen from the dawn of the universe and oxygen from stars. Air's invisibility hides a composition essential for life. Earth's solidity comes from silicon and iron, both born in ancient stellar furnaces. The mythological elements were not wrong in spirit. They were poetic foreshadowings of truth science would later illuminate. The great revelation of the modern age is that the universe's recipe is even more wondrous than the ancients imagined. The stars are the true hearths of fire, fusing hydrogen into helium, carbon, and oxygen. The cosmos itself is the great ocean, filled with rivers of gas and dust where new worlds form. The air we breathe is part of a galactic cycle, carried from star to star before settling into our atmosphere. The earth beneath us is stardust compacted into rock and soil. The myths, though not literal, captured something profound: that the world is unified and that the elements connect us to the larger universe. In this way, culture and science meet not as adversaries but as partners. Myths gave meaning before facts were known. Science provides understanding without stripping away wonder. When the ancients said the world was made of fire, air, water, and earth, they were offering a story that tied humans to the cosmos. When science says we are made of carbon, oxygen, calcium, and iron, it is telling the same kind of story in a different language. Both speak of connection, both of inheritance, both of belonging. So the next time you drink a glass of water, feel the warmth of fire, breathe deeply, or stand on the ground. Remember that these everyday experiences are echoes of ancient myths and modern truths alike. The elements of culture and the elements of science are two versions of the same great narrative. Long ago, people looked at fire, air, water, and earth and imagined that they were the primal ingredients of everything. They were not far off. The universe does indeed have a recipe, and whether written in myth or measured in starlight, it always tells the same story. We are part of it. Imagine for a moment a universe without stars. No points of light scattered across the night sky, no suns to warm planets, no galaxies glittering like jewels. Just endless stretches of hydrogen and helium drifting in the dark. At first it sounds quiet and serene, but beneath that stillness lies a startling truth. Without stars, the universe would be unrecognizable. Stars are not only decorations in the sky, they are engines of transformation. Without them, the cosmos would have remained locked in its earlier state, a bland sea of the simplest elements: Hydrogen would still dominate, with helium as a distant second and a sprinkling of lithium drifting unnoticed. That was the composition of the universe in its infancy, before the first stars flickered into being. If no stars had ever formed, it would still look like that today. In such a universe, there would be no carbon, no oxygen, no nitrogen, no iron. None of the elements that form planets, oceans, or living creatures would exist. The periodic table would stop after its first 3 entries, and chemistry would be a barren affair. The molecules that form DNA, proteins, rocks, or even water could never assemble. It would be a cosmos without complexity, forever stalled at the starting line. The absence of stars would also mean the absence of structure. Gravity might still gather gas into clumps, but without the heat and radiation of nuclear fusion to balance the collapse, those clumps would simply sink into themselves, forming dark, inert clouds or black holes. Galaxies as we know them would never shine. Instead of brilliant spirals and glowing clusters, the universe would be a silent fog, faintly laced with invisible matter. Consider what that would look like to any hypothetical observer. There would be no twinkling constellations, no guiding North Star, no Milky Way stretching across the sky. The night would not even be dark in the familiar sense, because darkness implies contrast against light. It would be a uniform blankness, as if the universe had never learned how to paint. No sunrise would ever glow on the horizon of any planet, because there would be no planets at all. Worlds require heavier elements, the ashes of stars, to exist. Without them, there could be no rocky surfaces, no oceans, no atmospheres, not even the faintest hope of a home for life. The very concept of time would feel different in a starless cosmos. Stars act like cosmic clocks, their lifespans marking the passage of billions of years. Supernovae punctuate history with brilliant bursts. Without stars, there would be no such markers. The universe would simply expand and cool, slowly and monotonously, with nothing to distinguish one era from another. Time would stretch on, featureless, a flat line instead of a melody. Life, of course, would never arise. Carbon, nitrogen, oxygen, phosphorus, and iron, all of life's essential elements, are born inside stars and released in their deaths. Without stars, the building blocks of biology would never exist. Even water, that most essential solvent, would be impossible, because oxygen would never be forged. In a starless universe, there would be no chemistry of life, no chance for cells to stir, no voices to ask questions. The cosmos would remain silent, not because no one was listening, but because no one could ever exist to listen. It is tempting to wonder whether something else might take the place of stars, some alternate source of complexity. Could black holes, forming directly from collapsing clouds of hydrogen, serve as engines of creation? But black holes without surrounding stars would simply sit in darkness, swallowing matter silently, without the spectacular jets and fireworks they produce in our universe. Without stars to feed them and galaxies to anchor them, even black holes would be lonely and unremarkable. The universe would have no stage for their drama. Even the cosmic microwave background, the faint afterglow of the Big Bang, would look different to any beings capable of perceiving it. In our universe, that background is eventually outshone by starlight, blending into the fabric of cosmic history. In a starless universe, it would remain the brightest feature forever, fading only as the universe expanded. The glow of the Big Bang would never be followed by the sparkle of galaxies. Creation would have begun with brilliance only to slide into eternal dimness. And what of planets? They too are children of stars. Rocky worlds require silicon, magnesium and iron, all forged in stellar cores. Gas giants require carbon and oxygen to form the compounds that seed their atmospheres. Without stars, planets could not exist in any recognizable form. The universe would be filled only with endless gas clouds, drifting and colliding but never settling into stable worlds. There would be no Earth, no Mars, no oceans or mountains. The concept of a landscape would never arise, because there would be nothing to walk upon. The absence of stars would also erase much of what we call beauty. Sunsets, nebulae, galaxies, all are products of starlight. The shimmering colours of auroras, the sparkle of snow, even the green of leaves are all effects of sunlight interacting with matter. Without stars, beauty would be impossible in its familiar forms. The universe would lack colour, light, and contrast. It would be a stage without actors, a canvas without paint. Yet even in such emptiness, physics would continue its quiet work. Gravity would still pull, matter would still move, and the universe would still expand. Hydrogen atoms would collide occasionally, forming rare molecules of hydrogen gas, fragile and fleeting. Over unimaginable spans of time, the universe would cool toward absolute zero, a quiet, featureless sea of particles. In its way, this starless cosmos would still be a kind of story, not one of creation and renewal, but of stillness and stasis. What makes this thought experiment so powerful is the contrast it provides. Our universe is vibrant because stars exist. They are the forgers of elements, the sculptors of galaxies, the parents of planets, and the enablers of life. Strip them away, and the cosmos collapses into simplicity, barren and uneventful. Hydrogen and helium alone cannot build the richness we see. It is only through stars that the universe has evolved from a thin mist into a dazzling web of galaxies, worlds, and living beings who can ponder it all. So the next time you look at the night sky, imagine it empty. Imagine no stars to count, no constellations to trace, no galaxies to admire. Imagine no earth beneath you, no water to drink, no breath to take. That is the universe we might have had. Quiet, sterile, and profoundly dull. Instead, we live in a universe of stars, a universe that has learned to cook, to recycle, and to create. Out of starlight came everything. Planets, oceans, forests, and even minds that ask what it all means. A universe without stars is a universe without stories. Ours, thankfully, is full of them, and everyone begins with a spark of starlight. The universe today feels full of energy and light. Stars shine across galaxies, nebulae glow with newborn fire, and supernovae scatter fresh elements into space. It is easy to imagine this as a permanent state, an eternal cycle of creation and renewal. But the truth is that we live in a cosmic springtime, a golden age when the recipe of elements is still being written. In the far future, billions and trillions of years from now, this alchemy will begin to slow. The ingredients of the cosmos will dwindle, galaxies will fade, and the birth of new elements will become increasingly rare. To glimpse this distant future is to see the quiet end of the cosmic kitchen. Star formation itself is already past its peak. About 10 billion years ago, the universe was far busier, with galaxies churning out new stars at a frenetic pace. Clouds of gas were plentiful, and the first great generations of stars enriched them with heavier elements, fueling more creation. Since then, the supply of raw hydrogen has slowly thinned. Stars still form today, but at only a fraction of the former rate. This decline will continue. Over the next billions of years, galaxies will consume or disperse their remaining gas, and fewer new stars will be born. The great factories of the cosmos will gradually go silent. As star formation wanes, so too does the creation of new elements. The heavy elements of the periodic table are not manufactured endlessly. They're made only in stars and in rare events like supernovae and neutron star mergers. Once the supply of new stars dwindles, so too will the production of fresh carbon, oxygen, iron, and gold. The elements already in circulation will remain, locked into planets, dust, and stellar remnants. But the universe will no longer replenish them in abundance. The great age of element making will fade into memory. The stars that exist will continue their slow work, each following its own path. The most massive stars will still burn quickly and end in supernova, scattering their riches. Medium-sized stars like our Sun will swell into red giants, shedding their outer layers and leaving behind white dwarfs. The smallest stars, red dwarfs, will persist the longest. glowing faintly for trillions of years. They burn their fuel so slowly that they may outlast the rest of the universe's visible stars, their faint embers illuminating the far future. But even they will eventually exhaust their hydrogen, leaving only cold remnants behind. Imagine that distant epoch. The sky will no longer blaze with countless points of light. Instead, it will be filled mostly with dark, cooled husks. White dwarfs turned black, neutron stars slowly fading, and black holes silently dominating the void. Supernovae will become rare events, perhaps only a handful occurring across the observable universe in entire centuries or millennia. Without explosions to scatter fresh elements, the circulation of matter will slow to a crawl. The cosmos will grow quieter, less dynamic, more still. In this future, the abundance of elements will remain fixed. No new carbon for forests that might never exist. No new oxygen to fill atmospheres. No new iron to forge into planets or blood. The atoms that already exist will persist, endlessly recycled but never replenished. Future civilizations, if any, will inherit only what the stars of today and yesterday have provided. The periodic table will become a closed ledger, no longer updated with fresh entries from stellar kitchens. Yet even in this far-off silence, the elements will endure remarkable journeys. Planets may persist for trillions of years, orbiting faint remnants of stars. Some will be swallowed by black holes, their matter added to those enigmatic vaults. Others may wander free through interstellar space, lonely worlds adrift with their elements locked in rock and ice. Dust may still drift through galaxies, slowly settling into clumps, but without the spark of star formation, it will never again ignite into brilliance. The ultimate scarcity of elements is tied to the fate of the universe itself. If cosmic expansion continues to accelerate, galaxies will drift farther and farther apart, their stars dimming into invisibility. Each galaxy will become an island, cut off from others, its supply of matter fixed. Over time, even within galaxies, the stars will fade, leaving only darkness. The chemical diversity of the cosmos will remain, but it will be a quiet diversity, frozen in place, no longer added to by new alchemy. Some speculative ideas suggest that in unimaginable timescales, exotic processes could continue element making in strange ways. Collisions between degenerate remnants might briefly spark bursts of fusion. Protons themselves may decay, erasing matter slowly atom by atom. But for all practical spans of time, the grand age of element creation will have ended. The cosmos will not stop existing, but it will stop changing in the vibrant way it once did. For us, here in the middle chapters, this knowledge is bittersweet. On the one hand, it tells us that we live in a special epoch, when stars still shine brightly and galaxies are alive with activity. On the other, it reminds us that everything is finite, even on cosmic scales. The stars will not cook forever, and the recipe of the universe will one day be complete. Yet perhaps that makes the present all the more wondrous. To live now is to live in a time when the universe is still busy with creation. Stars are still scattering new elements, planets are still forming, and life has had the chance to emerge. We stand at a moment when the cosmos is not too young, still locked in hydrogen simplicity, and not too old, faded into elemental scarcity. We exist in the flourishing season of the universe, the golden middle where complexity thrives. The future of elements is in many ways a future of memory. The atoms already born will remain as relics of stellar fire carried in rocks, oceans, and perhaps even in living beings elsewhere. Long after the last star fades, those atoms will still whisper of the processes that made them. Carbon will still tell of triple alpha reactions in ancient stars. Oxygen will still speak of helium fusion. Gold will still echo the crash of neutron stars. Even in the silence, the story of stellar alchemy will endure, etched into every atom. So when you look at the stars tonight, consider that they are not only lights, but also factories at work, creating the elements of the future. They will not do so forever. billions of years from now, their fires will dim, their recipes will end, and the universe will grow quiet. But here and now, in this brief, shining age, the cosmic kitchen is still open, and we are lucky enough to taste its results. Every story of the elements eventually circles back to us. We are not outside observers, gazing at the universe from a safe distance. We are the result of its long experiment, participants in a recipe that has been cooking since the dawn of time. Every atom in your body carries with it a history written in stars, explosions, and drifting clouds of dust. To reflect on this is to see yourself not as separate from the cosmos, but as one of its natural outcomes, as inevitable as the formation of galaxies, and as extraordinary as the spark of life. The recipe began simply. Hydrogen, the first element, filled the young universe like flour scattered across a counter. Helium, sprinkled in during the first minutes after the Big Bang, was the second ingredient. Alone, these were too plain to make much of anything. But gravity gathered them into stars and the cooking began. In the cores of those early furnaces, hydrogen was pressed into helium, and helium into carbon and oxygen. With each generation of stars, the recipe grew more complex. Supernovae scattered new elements, neutron star collisions sprinkled in rarities like gold and platinum, and clouds of dust swirled them all together. Out of this cosmic kitchen came the raw ingredients for worlds and eventually for life. Consider the inventory of your own body. Oxygen makes up most of your mass, not just in the air you breathe, but in the water that fills your cells. Carbon provides the framework for all of your molecules, from DNA spirals to proteins. Hydrogen, the most ancient element, is in every drop of water in you, connecting you to the very birth of the cosmos. Nitrogen threads through your DNA and proteins, a gift from stars that fused it in their hearts. Calcium strengthens your bones, forged in the late stages of stellar fusion. Iron courses in your blood, born in supernova explosions carrying oxygen through your veins. Even the trace elements, zinc, copper, iodine, phosphorus, each has its stellar origin, each is a whisper from an ancient star. It's easy to list these facts, but harder to feel their full weight. Imagine for a moment that each element in you has travelled across time and space. The oxygen you inhale may have drifted through interstellar clouds for billions of years before becoming part of Earth's atmosphere. The calcium in your teeth may have been forged in a star that lived and died long before our sun was born. The iron in your blood may once have been part of a star's core, compressed in a supernova and hurled across the galaxy. To be alive is to be a collection of these journeys, gathered into a single body. This realization transforms how we think about identity. You're not merely an individual, separate and small. You're a mosaic of cosmic history, a continuation of processes that began long before Earth itself existed. Life is the universe's way of reflecting on its own recipe, of tasting its own creation. In you, the stars are remembering themselves, arranged into thought and memory, into laughter and curiosity. The recipe also teaches us about patience. Stars take billions of years to cook their elements. Supernovae happen in a blink, but the enrichment they provide may drift for eons before gathering into a new system. Planets form over millions of years, life over billions. Nothing in this process is rushed. The universe does not hurry, and yet it achieves results of staggering beauty and complexity. To know this is to see our own brief lives in a new light. We are fleeting compared to the stars, but we are also their culmination, a spark in their long, slow unfolding. There is also humility in this view. The atoms that make you are not yours alone. They have belonged to countless other forms before, and they will belong to others again. The calcium in your bones may one day be part of a mountain. The carbon in your body may return to the air or dissolve into the sea. The hydrogen in your cells has been part of stars and may one day drift into space again. We borrow our atoms, using them for a time, before releasing them back into the cycle. The recipe is ongoing, and we are ingredients as much as we are results. Cultures throughout history have intuited this connection in different ways. Myths of earth, fire, water, and air captured the sense that life arises from elemental forces. Today, science has revealed the details, but the wonder is the same. Whether described in the language of myth or in the equations of physics, the message is clear. We belong to the cosmos. The elements in us are not accidents, but the natural outcome of stellar processes. In every age, humans have looked for meaning in the stars, and the stars have always answered by saying, "You are made of me." The thought experiment of a universe without stars shows us how unlikely our existence really is. If the cosmos had never lit its furnaces, if hydrogen and helium had remained unchanged, life could never have arisen. The fact that stars did ignite, did fuse, did scatter their ashes, is why we're here. Our existence is not guaranteed, but it is possible because of the way the recipe unfolded. We are the fortunate inheritors of that process, living in a universe that, against all odds, became complex enough to wonder about itself. And yet, the recipe is not eternal. In the far future, new stars will form more slowly, galaxies will fade, and the birth of new elements will cease. The universe will grow quieter, its ingredients fixed. Life, if it continues, will do so on borrowed atoms, reusing what already exists. But even in that distant twilight, the elements themselves will carry their story. Every atom of carbon, oxygen, and iron will still tell of the stars that made them. The recipe will remain etched into matter, even if the kitchen grows cold. Here and now, though, the recipe is still active. Stars are still fusing, still scattering, still enriching the galaxy. Planets are still forming, perhaps around distant suns, perhaps carrying their own stories of life. To live at this moment is to live in a universe still busy with creation. The kitchen has not yet closed, and we are lucky enough to exist while the fires are still burning. So when you take a breath, when you drink a glass of water, when you feel the weight of your own body, pause and remember what you are holding. You are holding starlight, condensed into form. You're holding atoms forged in fire, cooled and gathered into life. You're holding the recipe of the universe, completed only for a moment, before it changes again. We're not just part of the story of the elements, we are the story. Every heartbeat, every thought, every dream is an expression of the universe's long, slow cooking experiment. And when we look at the stars, we're not looking at something foreign or distant. We are looking at family, at origins, at the very same recipe that continues to unfold in us. To say we are made of stardust is not a metaphor. It is the most profound truth we know. We are the recipe, and the universe is still writing it. The story of the universe is, at its heart, a story of transformation. It begins with simplicity, a cosmos filled with little more than hydrogen and helium, drifting quietly in the aftermath of the Big Bang. At first glance, it might have seemed like a recipe destined for dullness, a universe locked in sameness, incapable of surprise. And yet, from that unassuming beginning came everything: galaxies, stars, planets, oceans, forests, and beings capable of wonder. The path from simplicity to complexity was paved by stars, those patient forges that transformed the raw ingredients of the early universe into the rich banquet of elements we know today. Stars are not just points of light scattered across the night sky. They are the silent chefs of the cosmos, cooking with time as their oven and gravity as their fire. For billions of years they have been gathering matter, compressing it, and igniting it into fusion. Inside their cores, hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, and onward the process goes, a slow and steady layering of new possibilities. Each element is not merely an entry on the periodic table, but a note in the music of existence, a contribution to the grand recipe that eventually gave rise to planets and life. When stars reach the limits of their cooking, they do not hoard their creations. Instead, they scatter them generously into space. Some stars shed their outer layers gently, like soft exhalations. Others end in dramatic explosions, supernovae that fling their enriched contents across galaxies. Rarer still are the collisions of neutron stars, cosmic cataclysms that create the heaviest treasures, gold, platinum, uranium, in bursts of energy so intense that they briefly outshine entire galaxies. The universe recycles these gifts tirelessly. Dust clouds absorb them, gravity gathers them, and new stars and planets form from the ashes. In this way, every atom in our world has been used and reused, passed along through countless generations of stars. Earth itself is a child of this recycling. Its iron heart, its silicate crust, its oceans and atmosphere, all are hand-me-downs from stars that lived and died long before the sun was born. The oxygen we breathe was fused in ancient stellar cores. The carbon in our bodies was stitched together in the triple alpha process billions of years ago. The calcium in our bones was cast into space by supernovae. The gold we wear and treasure was born in the violent embrace of colliding neutron stars. To live on Earth is to live on a planet made entirely of stardust, sculpted into rock, water and air by the patient work of cosmic time. And yet the story does not end with planets. Life itself is another chapter in the cosmic recipe. Every breath you take is an exchange of oxygen atoms, every heartbeat powered by iron in your blood, every thought carried along chemical pathways shaped by carbon, phosphorus and sodium. Your body is a mosaic of stellar memories, each atom carrying a history that stretches back billions of years. You're not a bystander to the cosmic process, but one of its outcomes, a living reflection of the star's generosity. Cultures long before modern science sensed this connection. They spoke of fire, water, air and earth as the elements of existence, weaving stories that tied human life to natural forces. Today, we use different words: hydrogen, oxygen, carbon, iron, but the underlying truth is the same. We're made of the cosmos, and the cosmos is alive in us. The myths of old were early drafts of the same great narrative science now tells with precision: everything is connected, everything is shared, and nothing is wasted. To recognize this is to see the universe with new eyes. The night sky is no longer a distant canopy of lights, but a family portrait. The stars are our ancestors, the forges that created the elements that allow us to live and think and dream. The galaxies are not foreign realms, but vast kitchens where the recipe continues. Even the dust drifting between stars is not empty debris, but the raw material of future worlds. The cosmos is not static, it is dynamic, recycling itself endlessly, with each generation of stars adding new richness to the mix. Yet this golden age of creation is not eternal. Billions of years from now, star formation will slow. Galaxies will grow dim. The birth of new elements will dwindle until the recipe is complete. The atoms already forged will persist, but no new ones will join them. The universe will grow quieter, its fires cooling, its kitchens closing. In that far future, the star's work will be remembered not in the light of galaxies, but in the enduring presence of the elements themselves. Even in silence, carbon will still whisper of stellar furnaces, oxygen will still carry the memory of fusion, and gold will still speak of neutron stars colliding in brilliance. But here and now, we live in the fullness of the story. Stars still shine, nebulae still swirl, and galaxies still sparkle with activity. The recipe is still unfolding, still scattering ingredients for worlds yet unborn, for lives yet to come. We exist in a rare and beautiful moment when the universe is neither too young nor too old, but just right for complexity to flourish. To think of yourself as part of this process is both humbling and uplifting. The atoms that make you were not chosen, but inherited, passed down through countless generations of stars, They will not remain yours forever. One day they will be released back into the cycle, perhaps to become part of a mountain, an ocean, or another living being. We are not the end of the recipe, but a moment within it, borrowing atoms for a time before returning them to the cosmos. Every breath is part of this cycle, every heartbeat, every drop of water, every handful of soil. All of it carries the legacy of stars. To live is to participate in the ongoing story of the universe, a story written not in ink but in atoms, not in pages but in the fabric of space and time. The recipe continues, patient and quiet, its results spread across galaxies, its flavours yet to be tasted in futures we cannot imagine. And so the story closes gently. Stars, those patient forgers, have given us everything: the elements of planets, the chemistry of oceans, the architecture of life. They have scattered their ingredients freely, writing the recipe of the universe with light and fire. To look at the stars is to see not just distant suns, but the origins of your own body, your own breath, your own being. Every heartbeat is a reminder of the quiet, cosmic recipe still unfolding, and every planet, every tree, every human life is proof that the universe, given time, learns how to cook. In the end, we are not separate from the cosmos. We are the recipe, the meal, and the memory all at once. And the story of stars is not only about them, it is about us too. For in every starlit night and every living breath, the universe continues to tell the same truth. Everything belongs, everything is connected, and everything carries within it the patient work of stars.